you already have downloaded the PDF for today, please replace it with this one, because there was a slight problem with the previous PPT. That's why it also got delayed. The class also got delayed. So if you already have, I don't know whether you have, but if you have already downloaded the previous PDF, please replace it with this one. All right, and the SMEs will soon post it also for you. The new link will be posted for you very soon. So if you already have downloaded the previous one, please replace it. Just one thing before we start. All right, so let's begin with our session. So yesterday we had seen and we had understood how the satellites are launched and the basic science behind the launch of the satellites. And then after that, one by one, all the different orbits and the kinds of satellites that are launched into those orbits, all these are the things that we had discussed. Now, to continue from there, the next topic for us is Lagrange points. Now, Lagrange points especially now become a very, very important topic. Why do they become an important topic? Last 2-3 years, we have seen that they have constantly been in news for one reason or another. So first and foremost, for example, now with Aditya L1 being launched, right? 2nd of September, Aditya L1 is about to be launched. It's almost ready for the launch. And Lagrange points will come in the news again because of that. Last 2-3 years have been like this. So there have been a few things because of this Lagrange points have been in the news. So what are Lagrange points? We'll try to understand, and what is the significance of these Lagrange points? Why are these Lagrange points important? Why are we launching satellites like Aditya L1 to L1? We'll understand all these aspects. Okay. So first and foremost, why in the news? So you'll find that there are multiple reasons for which they have been in the news. For example, the launch of James Webb Space Telescope. Have you heard of it? James Webb Space Telescope. One of the most important launches perhaps that has happened in the last 1 decade, one of the most crucial ones. And this James Webb Space Telescope was launched to a point called as L2, and this L2 is a Lagrange point. Then after that, we are now launching Aditya L1. Correct. So this Aditya L1 has been named as Aditya L1 because it is going to be launched to L1 point. And then another news was about something called as a Trojan asteroid. We found a new Trojan asteroid, and this was found at L4. The name is 2020XL5, and this was found at L4. So this was a new discovery that happened 2 years back. So we see that because of all these reasons, there is another one, just to name it, there is another one called as 2010TK7. And this basically is also found at L4. This was discovered almost a decade back. So because of all these things, we see that Lagrange points over the last 2-3 years constantly have been in the news. And frankly, I've been expecting question to come from Lagrange points. I think in the last year's classes also I said the same thing, that see, because of all these reasons, it's going to be in the examination. Before that also I've been saying the same thing, that because of all these reasons, it will be in the in your paper. But let's see. I hope that this time it comes and an easy question is asked from here. So understand this, that Lagrange points, because of all these reasons, they have been in the news. Now, first and foremost, what do we mean by these Lagrange points? So these points are very special points that are produced anywhere, wherever you have a two-body system, where one body is revolving around another body. In any kind of two-body system, there are these 5 special points that are produced, and these 5 special points are called as Lagrange points. So now, when it comes to Lagrange points and when it comes to the understanding of all these points, so this picture that you see right here on your screen, this is of Sun and the Earth, right? So Sun and the Earth also is a kind of a two-body system where Earth is revolving around the Sun. Similarly, with Moon revolving around the Earth, same 5 points will be produced. With any satellite revolving the Earth, the same 5 points will be produced. Just that, depending on the mass, the kind of points that are produced can be much more stable or much less stable. So, for example, when there are 2 bigger bodies involved, then it will be a bigger region of stability. So that's why keeping something or understanding those points, highlighting those points will be easier. But when you have a very small mass like a satellite, then these points will be kind of insignificant. But just remember that wherever you have a two-body system where one body revolves around another body, these 5 special points called as Lagrange points will be produced every time. So now, what exactly are these points? If you notice, there are 5 points that you can see, and they are very symmetrically arranged. Okay. So, for example, when you look at the points L1, L2, and L3, all of these 3 points, they lie on the same line. Correct. They lie on the same line. L1 lies between the Sun and the Earth. L2 lies behind the Earth. L3 lies behind the Sun. Correct. And then there are L4 and L5, which basically form an equatorial triangle, meaning that these angles, this is 60 degrees, and this is also 60 degrees, and same goes for these 2 points also. This is also 60 degrees. This is also 60 degrees. So these are points which are geometrically placed. Now, what are these points? Are these imaginary points? The answer is no. These are real points. These are real areas that exist in these kind of places, and these are very symmetrically arranged. Now, when it comes to these kind of points, which are which have this kind of an arrangement, again understand that wherever these areas are being produced. So, for example, when it comes to L1 and L2, these are points which are almost, and when it comes to the Sun-Earth system, these are points which are produced at almost 1.5 million kilometers from the Earth. Right? Almost 1.5 million kilometers from the Earth. So 1.5 million kilometers towards the Sun and 1.5 million kilometers behind the Earth. So in this manner, we see that there are all these points which are produced. Now, overall, when it comes to these Lagrange points, so first we have L1, L2, and then L3 behind the Sun. Then we have L4 and L5, which are symmetrically arranged between the Sun and the Earth, making a 60 degrees angle, making an equatorial triangle. Now, what is the significance of these points? Why exactly are we talking about these points? Because what we understand is that these are points which are balanced. All right, these are points which are exactly balanced between these 2 bodies in a manner that there is a region that is being produced, and if you just keep something at this region, right? If you keep something at this region, that thing will lie there for a very, very long time. So they are exactly placed at this particular point between these 2 areas. So now, when it comes to these points, so that's why these are areas of stability that are produced, and mainly because of gravity. Correct? These are points which are mainly produced because of gravity. So first and foremost, what are the forces that are acting here? First and foremost, what we know is that there is a gravitational force. All right, the forces that are acting here. First and foremost, you have the gravitational force. Correct? You have the gravitational force. Now, when it comes to the gravitational force, what we understand is that this gravitational force exists between the Sun and the Earth. Correct? Exists between Sun and the Earth. Right? So now, what happens is, because of this gravity, these kind of push and pull kind of a system is being produced. Now, there is another force that a satellite, like let's say when we talk about Aditya L1, there is another force that it is going to, right? There is another force that it is going to experience, and this is going to be the centrifugal force. It is going to experience the centrifugal force, and centrifugal force, basically we know that it's due to its own motion, right? The motion of the satellite itself around the Earth, that also basically produces this kind of an effect. So that's why we see that this is where the centrifugal force or the centrifugal force of the satellite will try to counterbalance the gravitational effect that is being produced. All right. So in a manner, you can say that the satellite's inertia counteracts the effective gravity. Now, beyond this, I don't want to go. Beyond this, I don't want to go because the calculations that we have to determine how exactly they are located, where exactly they are located, they are too complex. They're too complex for you to understand and too complex for even UPSC to even think of asking such a question. But what we see is that just remember that there are all these, I mean, for the forces, there are these kind of forces that will be produced, and not only for the satellite, but even for the asteroids that we discussed. Even for the asteroids, these kind of areas will be produced, or these kind of effects will be produced. So there will be a fine balance, there will be a kind of equilibrium that will start existing at these 5 points, and because of which these points become special. Now, when it comes to, let's say, Aditya L1, all right, now, and this is going to be very, very important now also. Now, when it comes to Aditya L1, what we know about Aditya L1 is that Aditya L1 is going to be lift off on September 2, and Aditya L1 is going to be placed at L1. Why exactly are we placing Aditya L1 at L1? What is the basic reason here? Understand this, that when you have something at L1, a point, or let's say an object, for example, Aditya L1, when it is at L1, it is always facing the sun. It is always facing the sun. So it's not that it is going to revolve around the earth. It is not going to revolve around the earth. It is going to revolve around that particular point. All right? It is going to hover around that particular point. So basically what happens here is that you have this point L1. Now as the earth moves, so for example, let's say when the earth goes from here to here, let's say the earth is here now. So when the earth is here, L1 also moves here, L2 also moves here, L4 would have moved here, L5 would have moved here, L3 would have moved here. So basically the entire system moves as a whole. So it's not as if that L1 is going to move around the earth. It is not going to revolve around the earth. L1 is a fixed point, and Aditya L1 is going to be hovering around that particular point. It will remain at that particular point. All right. So just remember this. So because of that, what happens is that when it comes to the point L1, anything at L1 will always be facing the sun. And what better point to keep than L1 then? Because we ultimately are going to study the sun. That's the basic objective of Aditya L1, that we want to study the sun, specifically the atmosphere of the sun and all the phenomena which are related to the sun. So that's why what we are getting there, I mean, once we are there at L1 point, this is something that will make it easier for it to exist there, and it can exist for a very long time. So for example, so that's why L1, once you have kept something at L1, then in that case, any point at L1 or anything at L1 will always be facing the sun. So that is the reason why Aditya L1 is being kept at L1. So anything at L1, so I'm just writing it out here. The significance of L1. Any satellite at L1 always will keep facing the sun. So in a manner, it will have a 24-hour access to the sun, and that's why it makes it easier for us to observe and study the sun, keeping Aditya L1 at L1. So that is the reason why L1 has been chosen for Aditya L1. Now, similarly, when we go to L2, what is the significance of L2? L2 is behind the Earth, and it will always remain behind the Earth. There's a reason why James Webb Space Telescope has been sent to L2, because L2 will be protected from the radiations of the sun, because the Earth lies in the way. If you look here, L2 lies behind the Earth, so it is always protected from the radiations of the sun. And when it comes to a space telescope like James Webb Space Telescope, it has a lot of very highly sensitive equipments, very highly sensitive components. The mirrors and the lenses also are very, very highly sensitive. So that's why you need to protect it from the harmful radiations of the sun. So it has a lot of shields, etc. as well, but there is a natural shield that acts for it, and that natural shield is the Earth. So that's why L2 becomes very, very significant for us from this perspective. So if I have to note down the significance of L2, so significance of L2 is that L2 lies behind the Earth, so is always shielded from the harmful radiations of the sun. All right. So that's why L2 becomes significant. Now, coming to, let's say, L4 and L5. In case of L4 and L5, L4 and L5 are said to be the most stable points. Out of the 5 points that we have, L4 and L5 are said to be the most stable points. And that's why very often L4 and L5 are the points where Trojan asteroids are found. So L4 and L5, significance of L4 and L5. They are the most stable among all Lagrange points. Okay, so that's the only significance, and that's why most of the Trojan asteroids for any planet are found here. Now, what do we mean by Trojan asteroids? We are talking about Trojan asteroids. So Trojan asteroids basically are the asteroids which are often found on L4 and L5, not only for the Earth, but even for Mars, even for Jupiter, especially for Jupiter. The number of Trojan asteroids at its L4 and L5 are very large. Why? Because obviously Jupiter is the closest to the asteroid belt. Also, it is very massive, so it has larger areas which are L4 and L5 points. So a lot of asteroids, what happens is that a lot of asteroids, they might sometimes come out of the asteroid belt, and while they are traveling somewhere, they might come to the L4 point or to the L5 point. And if they come to L4 or L5 point, they will just remain stuck here. They will just come here and they will remain stuck, and they can remain stuck for years. For example, the estimates that we have for the Earth Trojan asteroids is that they will remain here for the next 10,000 years. That for the next 10,000 years, this is their destination. They're going to relax here, and then after that, probably move on from here. So because L4 and L5 are very stable points, once somebody gets stuck, they can remain stuck there for a very long time. So that's why L4 and L5 have significance from that perspective, that these are the most stable points. Now, so that's why we see that Trojan asteroids are actually found there. So these are asteroids stuck at Lagrange points. All right, these are called as Trojan asteroids. So that is what we see about these Lagrange points. So it's a very complicated topic altogether about what Lagrange points are, and what we are touching is just the surface of what actually happens behind the scene, because that's too technical for you to understand and comprehend. And also, I don't believe that such questions can be asked beyond something like this. I don't think that they can ask a question from here. So where the gravitational forces of a two-body system like the Sun and the Earth produce enhanced regions of attraction and repulsion, where we see that there are 3 unstable points and 2 stable points. So you have L1, L2, and L3, which are unstable points, and the stable points are labeled as L4 and L5. So this is how we have. Now, if let's say you think of what is that L3, I mean, how significant is L3 for us? Then I would say it's not really significant, right? It's not very significant because it lies behind the sun. First of all, lies behind the sun, so it's almost impossible for us to communicate with this point. I mean, just imagine that between the Earth and L3, there is this giant ball of mass, giant ball of gases, that is the sun, and that's why you can't really see behind the sun. It's almost impossible for us to see behind the sun, so it's almost a blind spot. L3 is almost a blind spot for us sitting on the Earth, so that's why for us L3 does not really have a significance. Yes, unless you are an alien and you want to attack the Earth, then the best place to put your spaceship is L3. Like, come put your spaceship in L3, and then from there on come to the Earth and attack the Earth if you want to. So I'm very sure that none of you here have that intention. None of you here are from the supervillain tribe. So right, so these are some of these. So this is what Lagrange points basically mean. Now the last kind of orbit is GTO, or something which is called as geosynchronous transfer orbit. Geosynchronous transfer orbit, or GTO. Now when it comes to GTO, understand the significance of this particular orbit. First and foremost, we discussed that there are various different types of satellites that we launch. There are some satellites that are launched to the low Earth orbit, there are some launched to the medium Earth orbit, and then there are some which are launched to the high Earth orbit, right? Now, and we know that there are some launch vehicles that are lightweight. We discussed that PSLV is used for lightweight launches, and we discussed that GSLVs are used for heavyweight launches, right? Now, in any scenario, whether it is a PSLV or a GSLV or whatever it is, I mean, whether it is an Indian launch vehicle or a foreign launch vehicle, the launch vehicles cannot go beyond, let's say, 2,000, 3,000 kilometers, maximum 2,000, 2,500 kilometers, and not beyond that. So they can't go beyond it. All right, they can't go beyond it. They can only go up to that point. So now the problem is that we have to keep the communication satellites at where 35,786 kilometers. So if the launch vehicle cannot go beyond that, what do we do? So this is where we use the phenomena that is presented by the geosynchronous transfer orbit, where this is an orbit that transfers the satellite from the low Earth orbit to the high Earth orbit, to a 2,000 kilometer orbit to a 35,786 kilometer orbit, or let's say for simplicity 36,000 kilometers. So from 2,000 kilometers to 36,000 kilometers, the satellite is taken without the launcher going any further, because launcher cannot go. That's why just remember that if let's say you think why GTO is required, that why is GTO required? So GTO is required because launch vehicles can't go much further than the low Earth orbit. All right, launch vehicles cannot go beyond the low Earth orbit, and that's why GTO is required, and GTO will be transferring the orbit. So if you see this is where the transfer will happen from the low Earth orbit to the high Earth orbit with the help of GTO. You might have seen this with Chandrayaan 3 as well, correct? Although it's not geosynchronous transfer orbit, but that's also a transfer orbit, where what you might have seen is that from the Earth, when Chandrayaan 3 is launched first, you'll see that like this, it starts to increase its maneuvering, and then it goes like this, and then it starts to decrease here, correct? So something like this has happened. So this basically is where we see that this is also a kind of transfer orbit. Similarly, this GTO also is a transfer orbit, and in this scenario, from low Earth orbit to high Earth orbit, what we do is that at this point, where from there, when launch vehicle cannot go any further, at this point, an additional thrust is required. An additional thrust pushes the satellites further. Okay, pushes the satellites further. So this basically is what we see in case of a geosynchronous transfer orbit. So that's why these kind of phenomena, this is purely based on physics, purely based on how physics can carry this further, that how we calculate the perigee and the apogee, and based on the difference between the perigee and the apogee, we basically do the calculation so that once you push the satellite will be able to move on its own and reach the required point that you need. So this is how all these phenomena with regards to the orbits work. Now coming to the next topic. By the way, I see that you have asked a lot of questions. I'll take your questions in some time. Or okay, anything related to the orbits, if you have, we can just finish off that topic and then only move on to the next one. What is the distance of L1 from the Earth? It's almost 1.5 million kilometers. 1.5 million kilometers. Doesn't presence of Trojan asteroids mean Earth has not cleared its orbit? Wonderful question, Saloni. But I'll tell you no. And the reason why we'll say that it's not still about clearing the orbit is mainly because they are stuck because of Earth's gravitation. So what we are saying is that if something has an independent existence, it has an independent existence. For example, let's say if the Trojan asteroids, they were just revolving around the sun without even having any effect from the Earth, then in that case we would say that Earth has not cleared its orbit. But here what's happening is that these have been stuck at this point because of gravitation of the Earth. If they were not getting affected by the gravitation of the Earth, then we would say that it is not that the Earth has not cleared its neighborhood or the orbit. But wonderful question. Is centripetal force used in Aditya L1. See, for launching any satellite, centripetal and centrifugal forces will always be acting, all right? And in this case, the centripetal force will be the force of gravitation. The gravitational force itself becomes centripetal force, and the force due to the motion that we have provided, the thrust that we provide while the launch of satellite is done, that thrust acts as the centrifugal force, and the natural force, that is the gravitational force that acts on any satellite, not only Aditya L1, any satellite, is the centripetal force. Is the net force on Lagrange point zero? To keep things simple, we can say yes, that it is zero. But although what happens is that there will be a to and fro type of a system that happens here. So there will be a small positive and negative force that will keep acting there. But I mean, to keep things simple, as I told you, you can assume that the net force at this point is zero. Is James Webb Telescope situated in space? Yes, it is situated in L2. That's why it is called as a space telescope. Why don't a satellite revolve when placed at these points? That's what I told you, that because the forces. Just take that particular example that we had taken. That let's say you have a box and the forces from both the sides are equal. The pull from both the sides are equal, let's say, or the push from both the sides are equal. Then in that case, the box will not move. Same is happening here. What is the significance of L4 and L5? For us, not really a lot of significance, but just remember that these are points which are the most stable points. These are the most stable points out of all the 5 points, because keeping something at L1, L2 is not that easy. L3 is said to be the most unstable points, and compared to these 3 points, L4 and L5, these are very stable points. It takes 120 days to reach L1 point. It depends on what are we using, all right? What exactly are we using for it? So it's not necessary that it always take 120 days. Depends on the launch vehicle. Depends on how heavy or how bulky your launch vehicle is. Can we communicate with L3 via L4 or L5? Yes, theoretically we can, but just imagine that these points are very, very far away. Right? These points are very, very far away. So reaching L4 or L5 is also not easy. Just imagine that there was an asteroid all this while at L4, and we just discovered it 2 years back. So it has been at L4 for, we don't know for how long. It's not that it just entered here. Right? We just discovered it. So even though it lies at L4 and L5, we still haven't been able to discover it until 2 years back. So just imagine that these points, reaching these points or observing these points, are not that easy. But theoretically, the answer is yes. Mercury and Venus will not come in front of L1. They can, but it will not be a phenomenon that happens too often. It will just happen once in, let's say, hundreds of years. So that's why it is insignificant. All right. So let's move on. As the Earth, L1 will also move. So would be given also set L1 L1. Raghav, can you please rephrase your question? I could not understand your question. There's lots of L1 and these points are from the reference of the planet. Yes, you can say that there is another L1 between the Earth and Moon. There is one L1 between the Sun and the Earth. So these are 5 special points that will always be there between 2 points, 2 bodies where one is revolving about the other. So in a manner you can say that, yes. All right. So right. So the next topic for us are launchers. So when it comes to launchers basically will help us in launching the satellite. Until now, we have discussed about the orbits of the satellites, and we have discussed that how exactly we need these orbits and we need these kind of phenomena. What exactly happens while we try to launch any given satellite? Now, to launch any satellite, we need something that will launch that satellite, and this is called as launch vehicle. This is called as launch vehicle or the launcher. Now, when it comes to the launchers that India has, you'll find that there have been various launchers that India has used over the years. So we started with these ones, SLV3 and ASLV, the first two that you see on your screen, and then after that, PSLVs and GSLVs, etc., have also come. So overall, if you look at the number of launches that India has had, we divide the set of launchers into 3 phases of development. The first phase has been about historic and the retired launchers, the ones that we don't use anymore. Right? The ones that we don't use anymore. So you have 2 names here, SLV and ASLV. Then after that, we have the ones which are operational, the ones that we use today. We have PSLV, GSLV, sounding rockets, SSLV, and then we have GSLV Mark III that now is also called as LVM3. So just remember, for the sake of understanding, that GSLV Mark III and LVM3 are not different, because you might see these terms and you might get confused, because we were calling it as we are calling it as GSLV Mark III. We used to call it as GSLV Mark III, but what we have seen is that ISRO, especially over the past couple of years, has been calling it as LVM3 instead of calling it as GSLV Mark III. The reason why they have started doing that, the reason is that GSLV Mark III compared to GSLV Mark 1 and Mark 2, and we'll discuss this, is very different. All right, GSLV Mark III compared to GSLV Mark 1 and Mark 2 is very different, and that's why they don't want to call it as a GSLV, and that's why we have seen that there has been a shift in nomenclature from GSLV Mark III to LVM3. So just remember this, that LVM3 and GSLV Mark III are not different, both are same launcher. And then there are the ones which are under development right now. We have reusable launch vehicles, scramjet, and next gen launch vehicle. So these are the launches, these are the set of launches that India has. So let's have a look at all of them one by one. First, we have all the historic launches. Now, in the set of historic launches, there are 2 names that are very, very significant. One called as SLV, or satellite launch vehicle. Satellite launch vehicle. This was the first launch vehicle that India used, but with this launch vehicle, we could only launch a satellite up to 40 kg. Now, remember that this is where we are talking about late 1970s and early 1980s. 1979 is the first time we tested this. So back then, we did not have the concept of micro satellites or nano satellites and pico satellites and so on. There were only bulky satellites back then. So you could say that, okay, why are we not using SLV for the small satellites or the micro or the nano satellites? The reason is simple, that these are retired, and back then it was not useful. It was because most of the satellites that we used to launch back then were communication satellites. And communication satellites, as we have discussed, that these are very bulky satellites most of the time. So SLV was not useful as such from that perspective. But the most important fact is that at least it helped us understand the concept, helped us understand that how exactly the launch is supposed to be done, what is the physics behind the launch, so that now we could move forward. And this is what we do next. So for example, the next one that we had was ASLV. So ASLV, with ASLV, 150 kg satellite could be launched, but again 150 kg, although an improvement on SLV, was still not enough. Right? It stands for augmented satellite launch vehicle. So it had a better range this time. It also had a better payload capacity, but yet not enough. This changes when we come to the operational launches. Now, out of all the operational launches that we have, the first one is sounding rockets. Now, sounding rockets, I'm not sure whether you've heard of sounding rockets. Have you heard of sounding rockets? I'm sure that you've heard of PSLVs and GSLVs, but have you heard of sounding rockets? Some of you have. That's wonderful, but most of you are writing no. So now just imagine that an operational launcher about which you don't know last year completed 200 launches. So now sounding rockets has successfully done 200 launches for ISRO. Not only for ISRO, it also works for other aspects of technology as well. Also works for defense related areas also. But just imagine that it has completed 200 launches. Last year it completed 200 launches. So these many launches have neither been done by PSLVs and not been done by GSLVs, or not been done all the others combined. So more than all the others combined, the number of launches have been done by sounding rockets. Now, sounding. Do you know the meaning of this word sounding? Any idea about this word? Anyone who knows what is the meaning of sounding? Rohini is an example of this rocket. Yes, you can see that. So most of you are going in the wrong direction, that you are relating it to sound, but to meaning of sounding is to experiment. To sound means to experiment. So that's why these are sounding rockets. All right, sounding means to experiment. So that's why you don't really read a lot about them, because most of these are experimental launches. Most of these are experimental launches that, for example, let's say they have to test out a component, they have to do some kind of study, they have to do some kind of research. A lot of it is also defense related launches. So that's why we don't even see that in the newspaper, because the government does not tell about what exactly is happening. So that's why many of these launches do not even come in the news, and they do not really have the kind of significance that many of the other launches have. So that's why sounding rocket launches are not really in the news all the time, and that's why even though it has completed more than 200 launches as of last year, still we haven't heard of sounding rockets. So that's a sounding rockets because it does experiments. That's why the name sounding. So there have been multiple different variants. Three of the most important variants are these, but there are others: RH80, RH130, RH160. There are many other RH rocket or the sounding rockets here. Now about the sounding rockets, what it says is that these are 1 or 2 stage solid propellant rocket used for probing the upper atmospheric regions for space research. Now what we see here is that it is saying it is 1 or 2 stage solid propellant rocket. So what do we mean by stage? First of all, what do we mean when we say that it is a 1 or 2 stage solid propellant rocket? So stage means how many compartments of fuel do you have. So if let's say you have a 1 stage rocket, it means that there is 1 compartment of fuel. If it is a 4 stage rocket, it means that there are 4 compartments of fuel where the fuel is being carried. So stage basically just means how many compartments do you have which has been filled up with fuel. And solid propellant meaning that the fuel that you are using is solid. Just like for example coal, you can say that coal is a solid propellant because it is solid and it can be used as a fuel. So this is what sounding rockets are. Then coming to perhaps the most important launch vehicle for India, and this is Polar Satellite Launch Vehicle, or PSLV. Now, PSLV for the first time successfully, it was operational launch was done in 1994, and ever since then we have done tremendous number of successful launches. And the kind of success that we have seen with PSLV, you can say that PSLV has been the backbone of success of ISRO. A lot of successful missions, a lot of very complex and very significant missions. You'll find that most of them have been launched by this Polar Satellite Launch Vehicle. Most of them have been launched by Polar Satellite Launch Vehicle. So it is said to be Polar Satellite Launch Vehicle, right? Polar Satellite Launch Vehicle. So meaning that it is largely meant for polar satellites, largely meant for polar orbits or low Earth orbit. Correct? Most of the times, but it's not that always it will be used only for Earth observation satellites, or it will only be used for launching satellites into the polar orbit. For example, our beloved Aditya L1, the upcoming mission, is going to be launched using a PSLV. So that's why, although it is going to L1, still we are using PSLV for its launch. So you'll find that most of the very, very significant missions, if there is a possibility that we could launch it with the help of a PSLV, we have done that. Because we had discussed, if you remember, we had discussed in low Earth orbit that what you need for a PSLV launch is a lightweight satellite. That if the satellite weight is less than 1500 kg, then in that case we can make the use of PSLV instead of using any other launch vehicle. So that's why in case of Chandrayaan 2 we could not do that. Chandrayaan 3 we could not do that because Chandrayaan 3 is very bulky. So that's why PSLV could not be used. PSLV that's why could not be used. But whenever you have any satellite that is lightweight, that is at least less than 1500 kg, then in that case you'll see that ISRO has always preferred a PSLV. So for example, let's say Aditya L1. Aditya L1 I think is 1475 kg if I'm not wrong. The total payload weight is 1475 kg. So that's why PSLV could be used with for launching. For launching Aditya L1. Now, in case of PSLVs, as I told you, that PSLVs have been kind of a backbone of success of ISRO, because a lot of launches that have been done, successful launches that have been done, significant launches, strategically very, very important launches, they all have been done with the help of PSLVs. And if you look at, for example, data, let's say the data between 2007 to 2017, for 10 years, more than 40 launches, and PSLV did not really fail in any one of them. And this is very significant data, not only for India, but look at any launch vehicle in the world, you'll find that there is no launch vehicle that has been able to achieve such a feat. No other launch vehicle in the world has been able to carry on successful launches without any failure, without any problem for so long. And that's why PSLV also instilled a lot of faith of foreigners also in India, that they now think that, okay, fine, we can actually make the use of PSLV for launching our own satellites, and that's why it also becomes a huge source of revenue generation for ISRO as well. And many of the most significant of the launches that we have done, you'll find that these launches have been done with the help of PSLVs. This, for example, a very infamous cartoon that was published in the New York Times. This is something that was published in the New York Times, and this was a befitting reply that was given by Times of India. Now, what happened is that during the time of Mangalyaan launch, that was happening in 2013-14. At the time of Mangalyaan launch, Western media criticized India a lot, saying that India is a poor country. Why do you want to spend on a Mars mission? You should rather spend that kind of money on your poverty alleviation schemes. Put it on subsidies, put it on schemes and policies that you have for the poor in your country. Why do you want to have a Mars mission? What does a poor country like India have to gain with a Mars mission? And this happened in 2013-14. And again, with the help of a PSLV, we launched the Mangalyaan mission. And Mangalyaan mission became made India the only country to be successful in the very first go while going to Mars. There is no other country whose first mission to Mars has been successful. India is the only country. India is the only country whose first mission to Mars has been successful. That we did. It was a reply in itself, no doubt, because this is what they were showing. I mean, just look at this, that what exactly they want to showcase, that there is elite space club where they have all these people from in their suits and boots from various different agencies, and this is India. I mean, this is how racism basically works. That if you have to show an Indian, just show the person with a cow, and that's why then it signifies that person should be Indian. So. And it's, I mean, they might think that they are demeaning us. I don't see anything demeaning with a person standing with a cow. We always have had a very close relationship with our animals, with our plants, and that's why there is no shame. I mean, if they feel that it's in some way they are trying to demean, it's not. But this is a way they have always portrayed us. And just imagine that we are talking about New York Times, which perhaps is said to be one of the most reputed media houses in the world. And this is what they do. Later on, they obviously apologize because a lot of controversy was also created in all this. So. But I don't understand what that apology means. I really don't. Because if you really meant it, you would never publish such a thing, right? You would never publish such a thing, being such a reputed, so-called reputed media house of the world. And this is what you show. And unfortunately, you'll find that some of these Western media houses, they always have had this kind of stance. I mean, if you currently have become aware because of UPSC examination, you might feel that they keep writing an anti-Modi government kind of post. But it's not that it's only about the current government. You'll find that you just go back 30, 40, 50 years in time, and you'll always find that they have been writing anti-India posts. And not only anti-India, you say, let's say, anti-East, anti-Asia, anti-Africa, whatever you want to call it. So that always has been the stance, and it has never changed. It has not changed currently. It did not change in the past. And unfortunately, this is what they do. And this kind of cartoon being published, it shows the kind of irresponsible behavior that they have been showcasing all this while. But there was a good reply. This was 2017. If you remember, yesterday we discussed that there was PSLV C-37, where we launched 104 satellites in one single launch. Remember, we discussed this yesterday, that out of 104, there were 103 nano satellites. So this is when Times of India had published this, that now India is sitting inside with this record, and there are all these elite space clubs which are also knocking India's door. Because as I told you yesterday also, that 95 out of these 104 satellites were US-based satellites. So that also basically signifies this. But a good reply, right? A good reply. I think something very similar was published a couple of days back also in the context of Chandrayaan 3 again, because this cartoon now will haunt New York Times forever. The internet is a beautiful thing. You cannot erase the footprint of what you have done there. So anyway, so this is basically what we see. So we understand that PSLV has been very successful, and for that very reason, it also has been called as the workhorse of ISRO. We call PSLV as the workhorse of ISRO, because we have seen that most of the significant launches have been done with the help of PSLVs, not only with regards to the low Earth orbit satellites, but also with Aditya L1, with Mangalyaan mission, with Chandrayaan 1 mission, with Astrosat mission, with all the IRNSS satellites. For all these, what we have seen is that for all these satellites, we have used PSLVs. So PSLVs have been very, very important because of the success that they have shown, because of the revenue that they have been generating, and also because of the cost factor. Now, let me bring in another problem. Another success story of PSLV. Per kilometer cost of Mangalyaan mission is less than what you pay per kilometer perhaps in an auto rickshaw. So per kilometer cost to Mars with the help of Mangalyaan mission, with the help of this PSLV, is cheaper as compared to the per kilometer cost of per kilometer cost of an auto rickshaw. And something similar you'll see with the budget of even Chandrayaan 3. That even Chandrayaan 3 mission also, with the budget that we see, you'll find that the budget is lesser than the budget of many Hollywood movies. Many of the Hollywood movies have been made at a higher budget as compared to the budget that we had for Chandrayaan 3 mission. And there is one very significant thing here, because all these things now are in discussion because of all the launches that we are doing. For ISRO, what we have seen is that their budget also always has been very restricted. It's not that they have been given the kind of money that the Western space agencies have or they get from their governments. That kind of money has never been in India, and that's why we can't expect the government of India, I'm saying government of India, not current, not past, any government. So government of India cannot really afford to put a lot of money there, because they also have to put a lot of money in other schemes and policies for the betterment of Indian society. So that's why ISRO always has had restricted budget. They always have had not a very significant amount of money, but they have been able to do well even without that, and they have been able to make their plans accordingly and have been able to be successful with all that as well. And so, for example, let's say if we do a cost comparison, one data that I had read about was that one PSLV launch usually costs approximately $15 million, right? Almost $15 million in a basic launch. Whereas if you compare that to many of the Western launches, so for example, let's say if you talk about Ariane, so Ariane 5, for example, Ariane 5 is something that we use. I mean, when let's say we cannot use our own launch vehicle for some reason, we use Ariane 5, and the budget of Ariane 5 is almost $90 million per launch. Then after that, SpaceX, for example, SpaceX, I think it's almost $120 million per launch. So that's why the launch cost of the Western launches have been much higher compared to PSLV or even GSLV launch. Generally speaking, what we see is that a normal GSLV communication satellite launch costs almost $40 million. So overall, we see that what we have been doing, the launches that we have been doing, they have been far more cheaper as compared to the launches done by others. So that's why we see that all these also are a part of the success story of ISRO and also of PSLV. So what exactly PSLV looks like? It has 4 stages using solid and liquid propulsion systems alternately. So what we basically see is that if, let's say, a basic PSLV typically would look like this. ISRO will kill me if they see this picture, if they see this diagram. This is how I have reduced it to, right? So there are these 4 stages that you have. You have a solid stage, you have a liquid stage, you have a solid stage, and a liquid stage again. And this is where you have the payload. And this part is called as the core or the base. So solid and liquid, this is how alternately these fuels are arranged, and that's why this is a 4-stage launch vehicle. Now in this scenario, and rather in any scenario from that perspective, what we basically see is that always the first stage is solid, and then after that the arrangement can be different. First stage, but you'll see that most of the times first stage will always be solid, and last stage will always be liquid or cryogenic. Last stage will not be solid. Let's keep it this way. First stage, you'll see that most of the times, almost always, the first stage is solid, and the last stage is always liquid or cryogenic. Now, why do we always start with a solid fuel? Like, why do we always have solid as a first stage? What happens is that when you are launching the satellite, when you are on the Earth, the gravitational pull of the Earth is the strongest, correct? As you keep going outward, obviously the distance increases and the gravitational force decreases. So when it comes to the amount of thrust that you need, solid fuel will always provide the best amount of thrust, the most amount of thrust compared to any other fuel. So that's why we always prefer solid fuel as the first stage. And the problem with solid stage is that it is not easy to control solid fuel as much as you can control liquid fuel or cryogenic fuel. So that's why, because of that control factor, the last stage is never solid. Because if last stage is solid, placing the satellite into the orbit will be a very, very big challenge. So that's why the first stage always solid and last stage always not solid. Always. All right. So that is basically what we see here. That this is so why solid first stage. So answer is satellite is on the Earth. The gravity is maximum. Solid fuel provides more thrust than others. So that's why the first stage is solid. So the first stage is basically called as hydroxyl terminated polybutadiene, or HTPB. Then after that, the second stage that we have here, the second stage is called as unsymmetrical dimethylhydrazine, or UDMH. Then again, the third stage is again HTPB, solid. And then the fourth stage is something called as monomethylhydrazine, or MMH. So these are the 4 stages that we have in PSLV. All right, and one after the other, they are arranged. Overall, there are various different types of variants of PSLVs as well. We have PSLV CA, G, XL, DL, and QL. So if you look at this, these are the launches that we have done. So we started with something called as PSLV-G. It was also called as the standard variant of PSLV. And since 2016, it has not been used. This is 2016. So after 2016, this variant has not been used. And this has been discontinued, and it was replaced with these two. This was discontinued, and this was replaced with these two launch vehicles, PSLV, DL, and QL. And you'll see that after that, 2019 onwards, we started using PSLV, DL, and QL as well. And then after that, we have PSLV CA. So the pink one, if you see, this is PSLV CA. This year, there are 2 launches of PSLV CA that we have done. There will be another one that would have added if this class was happening 1 week later. Then this would have been 3, and this third one would have been this dark purple, that is PSLV XL. Because with the help of PSLV XL, Aditya L1 is about to be launched. Now, PSLV XL has been also very, very significant. The first launch that we did with PSLV XL was Chandrayaan 1. This was Chandrayaan 1. So Chandrayaan 1 was the first time when we did a PSLV XL launch. And PSLV XL, the name tells you that XL meaning, in a manner we say extra large in terms of clothes, you say XL is extra large. So same is happening here as well, that XL is the variant where the weight of the satellite that it can carry is the highest. Right? It can carry, this is the bulkiest of all the PSLVs. So that's why for the launches that are beyond 1200, 1300 kg, up to 15, 1600 kg, will be done by PSLV XL. So these have been the variants, and PSLV XL has been very, very significant. If you just look at the later half, you'll see that most of the launches that have happened thereafter, they have happened with the help of PSLV XL. So that's why PSLV XL has been very, very significant in the context of all the launches that ISRO has been doing. So we have all these different types of launch vehicles. So all these are the launch vehicles that we have used over the years. So PSLV CA and PSLV XL, these two I would say are the most widely used, and still they are the most widely used. When you have a lightweight launch vehicle or lightweight requirement, you'll see that in most of the cases, this is PSLV CA, and most of the heavier launches are done by PSLV XL. So these two have been the most significant of the ones, and then the others also have been used once in a while. After this, we have geosynchronous satellite launch vehicle, or GSLV. Now, in case of GSLV, a typical, forget about the actual picture, look at the picture that I am drawing for you. So this time there are 3 stages. All right, there are 3 stages in GSLV. You again have a solid stage first, then you have a liquid stage, and then after that you have a cryogenic stage. So this time things change. This time we have a new entry, and this new entry is cryogenic. So what we use here is a cryogenic fuel. Now when we say cryogenic fuel means what? The word, understand the word cryo. Whenever you see the word cryo, whenever you see the word cryo means extremely low temperature. Extremely low temperature. So wherever you have a scenario where we are talking about very cold temperatures, minus temperatures in -degree Celsius, then in that case it is called as cryo. So any technology that works at extremely low temperature will also be called as cryo. So now in case of cryogenic fuel, what we see is that cryogenic fuel has been very, very significant in the development of the GSLVs. And the story of cryogenic fuel goes back almost 30, 40 years. That first and foremost, when it comes to cryogenic fuel, there are only handful of countries in the world which have the access to cryogenic fuel. And it's not that cryogenic fuel is easy to make, and that's why it is not a public information. Right? It is not a public information that you'll not, nobody will tell you how exactly cryogenic is made, because cryogenic technology has been very, very significant, strategically very, very significant for many of these countries. So that's why you will not find a clear explanation to how exactly cryogenic works, but the basics are clear. So just understand that that what exactly cryogenic is, and as I told you that there are only a handful of countries in the world that know what cryogenic fuel is, and they know what a cryogenic engine is and how it works. And you can just count it. I mean, India has it, US has it, China, Russia have it, European Space Agency has it, and France has it. I think this is it. These are the only countries in the world that have cryogenic engine. I think Japan also has been successful here now. So Japan also has one. Apart from that, others do not. So only US, Russia, China, India, European Space Agency, France, and Japan. These are the countries which have the cryogenic engine. And apart from these countries, there is no other country that has an operational cryogenic engine. So cryogenic engine has been actually very, very important for India, very crucial also when it comes to the launches that we have been doing. Now, overall, when it comes to the cryogenic technology, you'll see that the the story of cryogenic technology in India also has been long and interesting. That in 1970s, for example, in 1970s perhaps was the first time that we could have had access to cryogenic technology. That in 1970s there were two instances. One, there was an instance when France had asked for India's help on a project, and Indian scientists did go. Indian scientists went there. They worked on that project, and it was very good success. And in return for the work that was done by the Indian scientists, a license of a Viking engine, we'll discuss that, which was required for liquid propulsion, was actually given to India. So it became very, very significant for India. Then there was another instance when, same again in the 1970s, there was another project on which France was working, and they again called upon Indian scientists. They again contacted government of India that we want to work with Indian scientists again. And this time, if Indian scientists would have worked with France, then India could have gotten the access to cryogenic technology back in 1970s itself, because France was ready. France had said that if you help, you'll get cryogenic technology from us. But we did not, because we were also working on a lot of our projects also, and at that point of time we thought that if we send our scientists to France, it would also mean derailing some of the projects that we are working on, and it will delay the various things that India has been working on. So that's why we can't afford to lose the scientists for another year or so. So we refused. So looking back into the history, we feel that perhaps this was a wrong decision, but it's very easy to say something retrospectively that it was a wrong decision then, but at that point of time you do not know what exactly was going on and whether it was actually possible for India or not, and we did not look ahead. Maybe is one of the criticisms, but ultimately the fact is that we did not get cryogenic. Then after that, in 1986, when a US based company was ready to sell cryogenic technology to India, but at a very high cost, a cost that India could not have afforded, and we had to politely refuse that we can't get technology for such a big cost. Then there was the third instance, where came our savior as always, USSR, then Russia now, and USSR was ready to provide cryogenic technology to India for free, without any cost, without any charges. They were ready to provide it to India, and already the transfer had started to happen. We were getting the access to the Russian cryogenic engines, but this is where US intervened. US intervened, and this was as a part of MTCR. This was as a part of MTCR, Missile Technology Control Regime. Missile Technology Control Regime. So now, according to the laws of Missile Technology Control Regime, an MTCR country is not allowed to provide a missile technology to a non-MTCR country. Now, Russia was an MTCR country. India, of course, was a non-MTCR country back then. Now, India is also a part of MTCR. But back then, India was not a part of MTCR. Russia was. So Russia was transferring this to India. So it was going against the laws of MTCR. So US intervened. US said that we are going to put sanctions against both of you if you are going to do this transfer. So both the countries had to stop. Unconfirmed, unofficial reports say that India and Russia still kept on working behind the scenes, and this is what also helped us in building the cryogenic fuel on our own, building the cryogenic technology, because this is where we understood when US did not let that technology transfer happen. We, in a manner, understood that we'll have to start working on our own, and this is what we did. And over the next 10 years, we were able to build cryogenic technology or build cryogenic engine in India. So this is how we see that it has been a long journey for India. That's something that we could have gotten in 1970s itself. It was 2001 finally when we were ready with our first version of a cryogenic fuel or a cryogenic engine. So cryogenic fuel basically is a fuel that works at extremely low temperature, a fuel which is a mixture of liquid oxygen and liquid hydrogen, where liquid hydrogen works as a fuel and liquid oxygen works as an oxidizer. So both of these, they work together in the context of GSLV. So now when it comes to GSLV, what we see is that there are three versions of GSLV that we have used: Mark 1, Mark 2, and Mark 3. Now if you look at Mark 1 and Mark 2, you'll find that the data for Mark 1 and Mark 2 are very, very similar. Correct? The height is similar, the number of stages is exactly the same, the payload carrying capacity is exactly the same, the lift of mass also is almost the same. Not a lot of difference there as well. But compare that to Mark 3. What you see with Mark 3 is that height is different, lift of mass is very high, the payload carrying capacity is also much higher. So that's why I was telling you that Mark 3, the scientists at ISRO do not call it as Mark 3 anymore. They have called it as Launch Vehicle Mark 3, because there is a significant departure from what was happening with Mark 1 and Mark 2. Also, with regards to the success rate, also if you see between 2001 to 2010, the success rate of GSLV was very poor. The success rate was not that good, and you'll find that almost more than 50% of all the launches that we have done between 2001 to 2011, they all failed. More than 50% of them failed. But then after that, we have been slowly and steadily, we kept on understanding it better. We kept on stabilizing the cryogenic technology, and now the missions don't fail. If you look at the last few missions, I mean, after 2012 to 2022, 23, we haven't lost anything. GSLVs also have now become stable, and especially that goes to the development of GSLV Mark 3, because while doing that, we also understood a lot of things, and now we started doing a lot better than what we were doing. So that is what we have seen with Mark 1, Mark 2, and Mark 3. Look at this question. Please read the question. This has been asked in your paper once. Read the question, and then after that, I'll launch the poll for you. All right. So I'm launching the poll. Please mark your answers. Good. So 64% of you have marked the correct answer. That's great. And then 8% B, 18% C, and 11% D. So let me just discuss this with you. With reference to India's satellite launch vehicles, consider the following statements. The first statement is PSLVs launch the satellites useful for Earth resource monitoring. This is fine, right? We have discussed this. If you remember, that low Earth orbit PSLV, remote sensing satellites or Earth observation satellites, we discussed that all these are related. So this is correct. GSLVs are designed mainly for launching communication satellites. This is also correct, because GSLVs go to geosynchronous or geostationary orbit, and this is where communication satellites are located. So this is what we discussed. So this is correct. Satellites launched by PSLV appear to remain permanently fixed in the same position in the sky as viewed from a particular location on the Earth. This is wrong. This is wrong. We discussed that when you are in the polar orbit, you take this 1.5 to 2 hours to complete one revolution. So from that perspective, you can't really say that it happens so quickly. I mean, that it can remain fixed. And which one remains fixed? Yes, Chaitanya, you're correct. Others, can you tell me which is the one that remains fixed? Which orbit? Which orbit remains fixed? Geostationary, right? Geostationary. So that's why geostationary, because stationary with regards to the Earth. So that's why permanently remaining fixed will be not PSLV, not by PSLV, but rather by GSLV when it is sending it to geostationary orbit. So that's why this is wrong. GSLV Mark 3 is a 4-stage launch vehicle with the first and third stages using solid motors and solid rocket motors, and the second and the fourth stages using liquid rocket motors. Is this GSLV Mark 3? This is PSLV. We discussed that GSLV is 3-stage, solid, liquid, and cryogenic. So there is no point in saying that it is 4-stage. GSLV, this is not GSLV Mark 3, this is a typical PSLV. So that's why 3 is wrong. So the correct answer will be 1 only. You have 3 in these 3 statements, and from one statement only you could have solved this question. It's an easy question. It's not a difficult question. Now, coming to some of the other aspects of our launches, one very, very significant part of all the launches that we have done has been about our Vikas engine. Now, Vikas engine basically is the design is based on the licensed version of the Viking engine, and Viking engine, this is something that belongs to France. This is the engine that I was talking about, that the license for Viking engine was given by France, and based on this Viking engine, we made the Vikas engine. You have you seen the film The Nambi Effect, Rocketry? Also won the awards in the national awards just a couple of days back. So many of you have seen it, many of you have not seen it, not a problem. Even if you have not seen it, doesn't matter, because anyway it is fictionalized. It's not entirely correct. I mean, what they have shown in the entire film is not entirely correct. But the crux of the movie is what was happening. So Viking engine basically is something that belongs to France, and France had given the license for Viking engine, and we developed Vikas engine from Viking engine on that technology, and we were able to do better. We actually have been able to do better. Today, Vikas engine is said to be one of the best liquid propulsion systems in the world, even better than Viking. So we took their technology and we were able to build better than that. So that's why Vikas. And Vikas, basically, the name Vikas has come from Vikram Sarabhai's name. So Vikram Sarabhai, one of the pioneers in space technology, one of the most significant names in space technology. And because of him, I mean, you can say that everything that happened in the early part of the development of space technology in India, you can basically say that it has been a big, big contribution from his side. So that's why Vikas was named after him, because Vik comes from Vikram, A comes from Ambalal, and S comes from Sarabhai. So that's why Vikram, Ambalal, Sarabhai, Vikas engine. So that's why Vikas was basically named after him. So Vikas engine used both in PSLVs and GSLVs in the second stage, in the fourth stage of PSLV, and in the second stage of GSLV. So we see that Vikas engine is used in all these cases, and other liquid propulsion systems also that India has. Everywhere you'll see that the design is based on the design of Vikas engine. So that's why we see that this has been significant. Then after that, there is this new launch vehicle that was introduced by India last year, and this is small satellite launch vehicle. Small satellite launch vehicle. So if you remember, we discussed about nanosatellites yesterday. We discussed the various points related to the advantages that nanosatellites have. So to launch these nanosatellites or small satellites in general, what one major hurdle for the launches over the past has been that we always have to wait. That why would we build an entire launch vehicle for launching a 10 kg satellite or a 20 kg satellite? So generally what happens is that whenever a big launch is happening, we try to just accommodate these smaller satellites along with it. So generally this is what happens. So now the problem is that for the nano satellites, pico satellites or micro satellites, etc., we always have to wait. We always have had to wait that, okay, fine, whenever PSLV or JSLV launch happens, we will also augment these satellites along with it and we'll send it along with. So this has been a problem with the small satellites. But looking at the market of the small satellites or the nano satellites in particular, ISRO understood that we need to take it away, or we need to take it away from or from our dependence on a big launch to always happen, so that these small satellites would be sent. And this is where the concept of small satellite launch vehicles comes from. That this is where we are going to have a launch vehicle that will be capable of launching any satellite up to 500 kg, into the lower Earth orbit. So it is a 3-stage solid propulsion stage. So just remember that in this, all the 3 stages that we have, they're all solid. But then I just told you that last stage should not be solid. So that's why there is something which is called as velocity trimming module. And this velocity trimming module is a liquid propulsion system based on MMH. Or monomethyl hydrazine. So that's why we see that here 3-stage, although it is 3-stage launch vehicle, but small amount of liquid fuel is kept with the satellite, so that ultimately you can place the satellite into the given orbit. So for the first time last year, the operations of the small satellite launch vehicle began. The first launch was not entirely successful. The launch of the satellite was successful, but just at the last moment, while placing the satellite into the orbit, there was a problem that happened, and the problem was that they were supposed to place the satellite into a circular orbit, but because of very small calculation error or some kind of computation error, instead of being placed in the circular orbit, the satellite got placed into an elliptical orbit. So that's why we said that it was not a complete success, because the launch of the satellite was success, but placing the satellite into the orbit was not entirely successful, because just moments before being kept into the orbit, it could not be kept into the entirely exact orbit that it was supposed to be. But again, the second launch has been completely successful, and there are many planned launches in the upcoming months. And not only now that the launches will not only be done for ISRO or something which is related to India or something that is being done by Government of India, but we'll see that a lot of private launches also will happen with the help of SSLVs. So this will help in the growth of private space market in India. It will help in the growth of startups in India. It will also generate a lot of employment opportunities. It will also help in a lot of revenue generation for ISRO. So there are all these things, and that's why the entire operation has been handed over to NSIL, that is New Space India Limited. We'll discuss about NSIL later, but so just understand the significance. What is the significance? First, provides independence to launching small satellites. Then source of revenue for the Government of India. Then helps in gaining the private space market, or to compete in the private space market. Growth of startups in India, or let me space based. All right. So there are all these things that you can see in the context of small satellite launch vehicle. The operations are to be seen by NSIL. Operations will be taken care of by NSIL. New Space India Limited. We'll discuss about NSIL later. Then after that, we have the scramjet engine. Now, when it comes to scramjet engine, just understand this, because now we are coming to the future. Until now, whatever we have discussed, these were all the operational launchers and what we have been doing currently. Now we come to what we want to do next and what is the future here. So one of the most significant part of the future discussions or the future launches that India wants to do is scramjet. Now, scramjet basically is a form of air-breathing jet engine. It is called a supersonic combustion ramjet engine. So SC stands for supersonic combustion ramjet engine. Now, in this kind of an engine, we are saying that these are air-breathing jet engines. Air-breathing jet engines. Now, understand the meaning of air-breathing jet engines. That what exactly do we do here? So just remember that for any combustion to happen, all right, for any fuel, for any rocket, any launch vehicle, you'll see that it's not only the fuel that is carried in the launcher, but apart from fuel, you also carry a lot of oxidizers. All right, you carry the fuel and you also carry some oxidizers. Now, the role of oxidizers would be that it helps in the combustion of fuel. Just remember that when it comes to oxidizers or any kind of combustion, let's say, without oxygen or without something that can act like oxygen, combustion cannot happen. That even if you are able to light a matchstick, you are able to do that because there is oxygen in our atmosphere. If let's say we were devoid of oxygen, if let's say our atmosphere does not have oxygen tomorrow, then what happens? First, we'll all die. But that apart, combustion cannot happen because there will be nothing to support combustion. So to support combustion, for combustion to happen, you need oxygen or you need oxidizers. So what happens now in all these launch vehicles? We carry a lot of oxidizers along with the fuel. That also increases the overall mass of the launch vehicle. That also increases the total weight of the launch vehicle. So that also is one of the problems that we have. That also is one of the issues, that it becomes very bulky because of the oxidizers. So we try to solve that problem partially with the help of scramjet, because these are air-breathing engines. So what happens is that instead of carrying the oxidizers, we will use the oxygen that we have in the atmosphere as an oxidizer. Something like this. That with the movement of, so let's say if the movement is happening in this direction, then you have the air that is coming into this engine like this. All right, this is coming from here. So now what happens is that this gets compressed here. It's already at high temperature because it is also moving very fast. So we have high temperature, and this air, of course, has a lot of oxygen. So as soon as it comes in contact with the fuel, the fuel comes in contact with oxidizers. The temperature is already high, so the combustion starts, and hence the engine will keep moving forward, and it will keep having the oxygen from the atmosphere as an oxidizer. So this is how we see the things working. This is how we see that scramjet works. Now, because scramjet works on oxygen we carry from the atmosphere, you cannot really use it in all the stages. Suppose that if you are thinking of a PSLV, that okay, fine, there are 4 stages and we'll keep using oxidizer in all the 4 stages. You can't, because after the first stage, while you are in the second, third, or the fourth stage, you already have come away from the surface of the earth, and there the oxygen levels are lower. Oxygen is thinner, so that's why you do not have a significant amount of oxygen to be used in the higher stages. So that's only perhaps for the first stage practically we can use scramjet, but even then it is significant because of the amount of oxidizer that will be saved, and because of which the entire launch vehicle becomes less bulky. Weight is less weight also means that you need to carry less fuel. You can carry more payload if you want. So there are all these advantages that we have with scramjet. So scramjet for the first time was tested in 2016. The first demonstration was done in 2016, and India again has become one of the very few chosen countries which have the scramjet technology. So it can effectively operate at hypersonic speeds. What do we mean by hypersonic? So as you can see here, that it says that it can operate between Mach 3 to Mach 6 speeds. The normal ramjet can operate between Mach 3 to Mach 6. This can operate beyond Mach 6. All right. So when we say Mach 1 basically is the speed of sound. Mach 1 is speed of sound. And in case of, let's say, when we talk about hypersonic, there are different terms. You have subsonic, you might have heard of supersonic, and then you have hypersonic. So subsonic is less than Mach 1. Less than Mach 1 is supersonic. Then between Mach 1 to Mach 5. Mach 1 to up to Mach 5 is called as supersonic, and more than Mach 5 is called as hypersonic. So here we are saying that this can actually operate at more than Mach 6. So that's why at hypersonic speeds, scramjet can actually work. So it has already been tested by ISRO already very recently. Also one demonstration was done, and not only for ISRO, and this is where the things become interesting, that it's not only something that is being used by ISRO, but at the same time you'll find that DRDO also has been working with scramjet, and the missile variant called as BrahMos, especially BrahMos 2, is also working on scramjet. It is also going to work on scramjet. So there also scramjet is being used. So that's why we see that it's not only something that is useful for space technology, but the development has also helped defense technology as well. So although developed by ISRO, but it is also being used by DRDO as well. Then after that we have reusable launch vehicle, another something that has been already tested by ISRO back in 2015. We carried out a successful test of reusable launch vehicle. So reusable launch vehicle means what? That the launch vehicle can be reused. So something like this. That what we want to do here is that after the launch of satellite is done, the launch vehicle will come back and it will fall back on the surface, all right, in the Bay of Bengal. We'll keep a point at Bay of Bengal, and at that point, the calculations will be done in a manner that it falls at that point, and then after that, it can be taken, retrieved, and it can be again used. So this is what reusable launch vehicle means. And again, we have been working on it recently. Again, this was also tested out. So we see that it is something that we are working on. And then lastly, we have NGLV. So NGLV is next generation launch vehicle. So the idea here is that now all the PSLVs that we are using, or even the GSLVs that we are using, will replace all these launch vehicles with one single launch vehicle called as the NGLV, next generation launch vehicle. So it should be a cost-effective 3-stage reusable heavy lift vehicle with a payload capacity of 10 tons to GTO. Meaning that it would be able to carry 10,000 kg to GTO. Until now, even with GSLV Mark 3, we only have a capacity of up to 4,000 kg to GTO. With this, we want to have a capacity of 10,000 kg to GTO, and this is where we are working. And it will have a semi-cryogenic propulsion. Semi-cryogenic propulsion, meaning that there will be kerosene mixed. Again, this also was tested a couple of months back. In the month of May, a testing has been done with the kerosene-based semi-cryogenic propulsion. We basically are getting ready because reusable was tested recently. Kerosene-based semi-cryogenic was tested recently. So all these things, they hint towards that we are building up to NGLV. So NGLV basically will be the next generation launch vehicle where we will be able to take care of all our needs. Then lastly, we discuss about the fuel, that you have HTPB, which is the solid fuel. Where are we using HTPB? We are using it in the first and the third stages of PSLV, first stage of GSLV, and all three stages of SSLV. Then after that, we have the UDMH, or unsymmetrical dimethyl hydrazine, where you use it for the second stage and second and the fourth stage of PSLV, and second stage of GSLV. And then after that, we have MMH. MMH is basically sorry. So we are using UDMH in the second stage of both GSLV as well as PSLV. And then we have MMH. MMH is being used in the fourth stage of PSLV, and the velocity trimming module of SSLV. So this is where MMH is being used. Then we have LOX and LH, where you have the liquid form of oxygen that works in the cryogenic engine and around minus 150 degrees Celsius. That's the temperature. And liquid oxygen basically is the oxidizer. It is the oxidizer that is being used in the cryogenic engine. And then LH is the liquid form of hydrogen used as fuel in the cryogenic engines, where the temperature of around minus 250 degrees Celsius is required for liquefying hydrogen. And then we have MON. MON stands for mixed oxides of nitrogen. And mixed oxides of nitrogen basically are used as oxidizing agent, or they're used as oxidizers in the liquid propulsion or even solid propulsion systems. So this is where we see that all these are the different things which are related to the launch. So let's take a break here. The time right now is 7:47. Let's be back by 8 o'clock. And meanwhile, if you have any doubts, please post your questions. When we come back, I'll first take your questions, and then after that, we'll move on to the next part. Welcome back, everyone. Currently, which parts of a launch vehicle this is destroyed for us to develop a reusable launch vehicle? See, every part. I mean, what you see is that each and every part is expendable, meaning that it can be used only once, and after that, it can't be. So, in reusable launch vehicle, the entire set will be reusable, is what we are saying. What is the difference between GSLV and SSLV? They're completely different. GSLV is a very bulky, uses cryogenic, used for your communication satellites, goes very far. SSLV, small satellite launch vehicle for smaller satellites, only solid fuel. So, significantly different. Do we have to mug up these? Mug up is a wrong word. I would say that you have to understand what we have discussed and then learn and remember, not mug up. Because if you mug up, you forget. How much depth in studies is required in science and technology? See, if you look at the past papers, many a times it has been very hard to comprehend what level they want the students to go to. But more or less, the level that we have taken in these lectures, that's the most about it. I mean, I don't think that they can go beyond that. So, if let's say they go up to level 1, what I'm doing is we have taken it to level 1.5 or level 2, so that you have a better understanding of all these things, much more significant knowledge of all these things, and you should not be missing out on anything. So, but this is, you can say, the ceiling. Beyond this, I don't think it's required. Why do we use insulators inside of PSLVs and GSLVs? See, insulators will be required to ensure that each and every component can work independently, does not get affected by others, and also by the outside temperature, because outside ambient temperature also, because of the air friction will be very high. So from that also you need to do all this. You need to insulate from there as well. How does Aditya L1 revolve around the sun along with the Earth while revolving around the L1 point? So basically, what happens is that this will be motion like this, that it is revolving around L1 and it keeps moving on like this. That it keeps on moving like this. You can say in a manner. This is how the movement will be around the sun. So this is how it will keep on moving. Do we need to learn the expanded form of the fuels? No, you don't need to. Does cryogenic technology contribute to pollution as it uses up oxygen? No, it's a very insignificant amount of oxygen. It's a very, very insignificant amount of oxygen, so it will have no effect whatsoever. If at all, it will have a positive effect because you don't have to carry the oxidizers, which are chemically more harmful as compared to using oxygen. Please explain space-time. See, space-time basically is the structure of the universe, as we say. Now, overall, what happens is that when we mention the dimensions of any given space, you always talk about the length, breadth, and the height, correct? So those are the dimensions of space. Those three are called as the dimensions of space. And then after that, when it comes to time, time is taken as a fourth dimension. Now, why time? Because we know that everything in the universe is moving. So, for example, if you are looking at, for example, let's say the Earth is rotating and revolving. So, if Earth is here at this instance, the next instance its location has changed. So that's why when you define where exactly an object is, where exactly a celestial body is, you cannot only define space, but you also have to define time. That it was here at this moment, it is here now, it is going to be here at the next moment, and so on. So that's why when we define anything in the universe, we define it in terms of space and time, and not only the space. MMH is used where? We discussed that MMH is used in the fourth stage of PSLV, right? In the fourth stage of PSLV and in the velocity trimming module of SSLV. How to remember these facts? See, some of these facts that we have discussed, only that much is required. Beyond that, please don't go. And these things, I mean, some of these things are basic information about all these technology that we are discussing. So only that much is required, not beyond that. Why each and every country is in the space race? What is the main reason of benefit in launching various types of missions? Such as yesterday, it is found that Chandrayaan 3 has found some amount of oxygen in the moon, and how will it benefit our country? So, see, why space race? First of all, because we understand the value of space technology. We know that there are a lot of ways in which it has been helpful. So, for example, while developing all this technology that will help us on the moon or it will help us on various other celestial bodies, at the same time, it does help us also acquire technology or develop technology that will help us in future in other aspects as well. That when we launch, let's say, an Earth observation satellite, or when we launch a communication satellite, these are satellites. When we launch, it is always going to be useful. So, when we look at any technology or let's say any mission, you should not see the mission only in the light of that one mission only. You have to see it from the perspective of technology and how technology overall is going to help in the future and in other aspects as well. And then about finding, let's say, something like oxygen, or even it was reported that it has also found sulfur. Yesterday, it was reported that it has also found sulfur on surface of moon. Then the temperature variations that they found on moon. So all these will simply help us in understanding moon better, understanding the origin or the developmental phases of moon, and that will give us a better understanding of the solar system and the universe and everything that exists. So overall, it will help in research, and it's not only application for Indian society, but an application, science-based application as well. India developed Elon Musk rocket method can reuse again and again. So yeah, I mean SpaceX has been using it since 2019, but our method has been not based on it. It has been developed independently. can you explain cryogenic again? So just remember about cryogenic, that when you say something is cryogenic, first and foremost what it means is that it is going to work at extremely low temperatures. Now the cryogenic fuel that we use is basically liquid hydrogen. All right, it is liquid hydrogen, and liquid hydrogen, meaning if you want to liquefy hydrogen, liquefying hydrogen can only happen at a very low temperature below minus 250 degrees Celsius. So you will have liquid hydrogen which will be mixed with liquid oxygen, and these two together they become the cryogenic fuel. Now this cryogenic fuel can be used in space vehicles, it can be used in rockets, it can be used in aircrafts. You'll find that even in World War II, cryogenic engines were being used by countries like France, and then it can be used wherever you want. The efficiency that it provides is very, very good. Efficiency of cryogenic compared to others is far better, and that's the reason why we want to use cryogenic engine altogether. How can we generate money from launching satellites doing research on space? So because you will be doing a lot of private launches, you'll be doing launches for a lot of different countries, you'll be providing services and products to various different organizations, so that will also help you overall in generating the revenue. Space is also the fourth dimension of modern warfare and other development programs. Yes, absolutely correct. Right, haven't understood Kepler's third law from yesterday. So third law says very simple thing. Let's see, you have the sun like this. Suppose you have one planet here and you have one planet here. This planet to complete one revolution will take less time because it is covering lesser distance altogether, and this planet will take more time to cover this revolution, right? So this is what the third law says, that if you are near the sun, you will take less time to complete one revolution. If you are away from the sun, you will take more time to complete one revolution. That's it. That is what it is saying. And then there is the mathematical relation that comes out of it, that p square is proportional to aq. But more than that, this is what it says, that when you are near, you are you take less time. When you are away, you take more time. Aditya L1 has to travel 1.5 million kilometers to reach the Lagrange point. Will it not require a lot of fuel for it? So as I told you that the launch vehicle does not go beyond 2,000 kilometers. So launch vehicle carrying the fuel does not go beyond that. Rest is all on the shoulders of physics. Rest is all on the shoulders of physics, and how the concepts of physics, the concepts of gravitation, of centrifugal and centripetal forces, how we calculate all that to ensure that it reaches the given point. Something which is also called as gravity assist will be used, so that you take the assistance from the gravitation of the various celestial bodies, so that they will provide the kind of push and pull that is required for it to travel further. Right. So I think I've answered the questions that I had here. Suppose we are living in a far planet. What is our age criteria? I'm not sure about your question. Can you please rephrase your question? Though India is not well developed in terms of poverty reduction, how is it advantage to invest in space technology? See, when you invest in space technology, you help the country anyway. Because employment generation aside and the startups, etc., the private sector aside, ultimately space technology has helped our agriculture. It has helped in disaster management. It has helped in resource monitoring. It has helped in finding oil resources. It has helped in finding mineral resources. So ultimately, it has helped. So all these things, they add to the Indian economy. So it's not always. That's why when it comes to countering poverty is not always about giving money to the poor. It's also about how you can support the poor in various different ways. And these are all the various different ways in which you can support the poor. At L1 point, gravity of both the sun and the earth will be same or different. You can say that both will be able to balance one another. How moon and the sun missions help? It's simple. They would help because you are developing the technology better. You are doing something better, and it's not going to help directly. I mean, if your question is about how does it help the Indian society directly, so the answer is no. It does not help the Indian society directly. But there are so many other programs that do. Just understand the context. Understand the context. We have done more than 100 launches that are related to some kind of space application for Indian society, and there are 4 or 5 such launches that we have done which are related to space science research. So that's fine. I mean, just 5% of your money is going into these kind of research. Rest 95% is going directly into the application-based areas. And at the same time, the kinds of technologies that we are developing, it also helps in further development of technology which will be used somewhere. For example, Scramjet. Scramjet was built for our space research, but now you are using it for the missiles as well. So it's not that when you develop technology, that's why I told you that don't see technology in the context of only one project. That only one project will be benefiting from there, and then after that, the technology will never be useful. No. Once we develop it, we'll have a better understanding of everything, and that in one way or the other helps. So you may not see a direct impact on the Indian society, but ultimately it does have an indirect impact on a positive impact on the society. All right, so let's move forward. So next, we move on to the next topic, and that is Indian Space Research Organization, or ISRO. So until now, we have most of the technology-related aspects is what we have discussed. Now, when it comes to understanding of ISRO, this one statement, it becomes extremely important. The vision. The vision of ISRO is to harness space technology for national development while pursuing space science research and planetary exploration. Now, this one sentence sets the context beautifully. That what exactly does ISRO do? Harness space technology for national development. This is the primary objective. And then while pursuing space science research and planetary exploration, meaning that our primary goal will always be national development. Our primary goal will always be to help the Indian society. But beyond that, we will be carrying out the other experiments as well. And that's why when you count the number of such experiments or count the number of missions which are based on space science research, there are hardly any. Right? Chandrayaan 1, 2, 3. Even Chandrayaan 3 wouldn't have happened if Chandrayaan 2 was successful. So Chandrayaan 1, 2, 3, Aditya L1 upcoming, Gaganyaan upcoming, Astrosat, Mangalyaan. That's it. So you can very easily count that there are only 7 out of which 5 have been launched and 2 are about to be launched. Apart from that, all the other missions have been based on some kind of application, whether it is about communication, whether it is about strengthening our navigation, or whether it is about the various different types of Earth observation satellites that we have launched. So when you look at the context, there you understand that the major objective, the main objective has been national development. The mission statements are not that important. It talks about all the different things that ISRO does: design and development of launch vehicles or satellites, the various programs that we have, the societal development applications. So that is basically what it says. Now, overall, when it comes to the organizational structure of ISRO, this is the structure that we have. Now, not everything is important, but there are certain units that can become important for you. So we'll focus on those units. These, for example, these all units will be important. Apart from that, these two will be also important. And then you have in space that I believe can be important. So just in one line, understand the role of all these things, all these units. So first you have Vikram Sarabhai Space Center. Now Vikram Sarabhai Space Center, VSSC. Vikram Sarabhai Space Center is where the design and development of the launch vehicle is done. And everything related to launch vehicle and all the associated technologies. Everything with regards to the launch vehicle everything with regards to the launch vehicles will be done at Vikram Sarabhai Space Center. Not only the development of launch vehicles, but even the smallest of the things. For example, what kind of paint will be used in the launch vehicle, even that paint will be developed at Vikram Sarabhai Space Center. Then after that, we have LPSC, that is Liquid Propulsion Systems Center. Now this is where the fuel development happens, or fuel fabrication happens. So everything with regards to the fuel, everything about how exactly are we going to use the fuel, this is where you'll see that LPSC is going to work. Then we have SDSC, that is Satish Dhawan Space Center. This is where we do all the launches from. There are 2 launch pads here, and that's why we say that this is launch base infrastructure. This is the launch base infrastructure for India. There are 2 launch pads here. So sometimes first one is used, sometimes the other one is used. Then after that, you have URSC. URSC is UR Rao Satellite Center. It was also called as ISAC before, ISRO Satellite Complex. It was called as, now it has been renamed as URSC. Now this URSC is where the satellite development takes place. The satellite development takes place at URSC. Then after that, we have Space Applications Center. Space Applications Center is where many different components, instruments, sensors, all these things that are supposed to be used in a satellite, all these equipments, all these smaller components, they will be developed at Space Applications Center. So various components, instruments, sensors, etc. They are developed at Space Applications Center. Then after this, we have NRSC. NRSC is National Remote Sensing Center. National Remote Sensing Center. And the role of National Remote Sensing Center is the data processing. The data processing of all the data, all the pictures, videos, the data that are received from the Earth observation satellites. So every bit of data that we receive from the our satellites, our remote sensing satellites, all that data processing is done at National Remote Sensing Center. All right. Processing of remote sensing data. Then after that, finally, we have HSFC. Now, all the other units, they have existed for a while. They have been here for easily 10 to 15 years, or more than that. I mean, almost 20 years, you can say. But HSFC is a new addition. This was added to the list of units only in 2019. And HSFC stands for Human Space Flight Center. And that is exactly what it is supposed to do. That it is going to work on any human space flight that India takes. So right now, it is working on the Gaganyaan mission. It is working on the Gaganyaan mission. So Gaganyaan plus all the future human space flights. So this is what HSFC is. So all about all these units, just know in one line that if at all a question has to come in the prelims, because now in the context of Chandrayaan 3, in the context of Aditya L1 and so on, you'll see that some of these units will be in the news as well. So that's why you should just know about their basic function. Then after that, we have Antrix and NSIL. These two are called as commercial arms of ISRO. We call them as commercial arms of ISRO. Now, why commercial arms? Because anything with regards to the marketing, the revenue generation, the sales, or anything related to the commercial aspects of the launch, each and everything will be looked after by these two organizations or these two units. Now, out of these two, Antrix has been here for a while. Antrix again has been here for, you can say, easily now almost 20 years. Now, but NSIL is a new addition. NSIL was again formed just a few years back in 2019. And when NSIL was also added as a commercial arm of ISRO, the questions were also raised. There were some questions that were also raised, that why was NSIL required? If we already have Antrix, so in the presence of Antrix, why do you need NSIL? What was the requirement? So there was some controversy happening around it also, and the government had answered this question in the parliament. And what the government said is that Antrix is supply based, and NSIL will be demand based. So Antrix will be supply based and NSIL is demand based. Now, what's the meaning? What do we mean by supply based and demand based? So what the government said is that Antrix will be working in the areas where we already have something, and somebody comes to us to purchase something or to ask for some kind of service which already is with us. But now when it comes to NSIL will also take new requests. So for example, let's say Antrix is like going to a grocery shop. Then you go to the grocery shop, you ask for something. If you have it, you get it. If they don't have it, you don't get it. Simple. So that is the role of Antrix now. That it is becoming supply based. That it will be working on everything that ISRO has, and somebody comes to us and asks for something that ISRO has done or can provide as a product or service, we'll do that. But in case of NSIL, if you have a new request, you will come to NSIL. You will place your order, and then they will try to fulfill your order. So that is what we mean by demand based, and that is what they said, that this is what the difference between Antrix and NSIL is supposed to be. And then lastly, we have InSpace. Now, InSpace also is a very new addition, added just in 2020. Before 2020, there was no InSpace. Now, InSpace basically is to help the private sector. Right? It is for helping the private sector. So that's why it is Indian National Space Promotion and Authorization Center. So Indian National Space Promotion and Authorization Center. So it has been named as InSpace. Now, InSpace basically is for helping the private sector. It is basically for helping the private sector. It is going to help the private sector, and it will help. It will provide the support that is required, the authorizations that are required, the clearances that are required for the private sector also to work along with ISRO. So this is a basic infrastructure of ISRO. This is how you have all these various units, and they all have been working as a part of ISRO. Now, if you look at the map, you'll find that most of the centers of ISRO, they lie in the south. Correct? Most of these lie in the south. So also understand why, because apart from, let's say, just one, that is Space Application Center. Apart from Space Application Center, everything else you'll find that they are in the southern part of the country, and for a very simple reason: the launch that we do is here. Right? The launch that we do is here. So now, if let's say the satellite was being prepared in Delhi, and it had to come all the way to Sriharikota in Andhra Pradesh from Delhi, it would be a big logistic challenge, right? It will be a big logistic challenge. So it's not that easy that you just keep the center anywhere and you can manage from there. That's why you see that the headquarters of ISRO is also in Bangalore, and then after that, in all these other areas, I mean, most of the other things are also, many of these things are in Bangalore, and then after that there are other centers. So for example, so headquarters is here, then ISRO Satellite Center, or what has become URL Satellite Center, is here. LPSC is here. So all these are present in Bangalore. And then after that, the others, for example, let's say even HSFC. HSFC now is also in Bangalore. And then after that, you have some, for example, Vikram Sarabhai Space Center is in Thiruvananthapuram. And then after that, you have NRSC in Hyderabad. So apart from all these, you see that most of the others, most of the centers are in Bangalore itself for better coordination, of course. Now, there's one more discussion happening right now, and this is about the Kulasekara spaceport. Now, when it comes to Kulasekara, understand why Kulasekara is also being chosen as a future space port for India, or future launch-based infrastructure for India. Right now, our launches are happening from here. This is where you have Sriharikota. So this is where we have Sriharikota. And now what we want is that apart from Sriharikota, we also want to build another launch-based infrastructure at Kulasekara. And again, just a couple of months back, this was also in the news. And this also was being discussed. So understand a couple of concepts here. That why are we launching the satellites only from where we are launching the satellites? All right. So if let's say the first question is why Sriharikota? Any idea, anyone who knows why have we chosen Sriharikota? Okay, near the sea, proximity to the sea, coastal place, that's correct. Near the equator, yes. So two important things, all right? Two important things. One, that it is located in the eastern coast. So what you will find is most of the launch sites across the world, not only for India, across the world, most of the launch sites are either on the eastern coast or are located on islands, either islands or east coast. Why east coast? Why do we use it in the east coast? East coast mainly because the launches that we do always are done eastward. The launches are always done eastward. Now suppose that we had taken a point in Karnataka or a point in Maharashtra, and we wanted to do a launch from there. So if we were doing a launch from, let's say, coastal Karnataka, then it would mean that from coastal Karnataka you will have to run eastward over the Indian landmass. So just imagine that if something goes wrong, if let's say it is about to fail and fall, then in that case it can be a big trouble if it is going above the landmass, right? So that's why we would try to ensure flying above the Indian landmass. So that's why eastern coast has been chosen and not the west coast. So east coast, why east coast? East coast, as launches are always done eastward. And do you know why? Why do we launch it towards the east? Yes, Amrit, you are correct. Abhishek, you are correct. Raghav, correct. Deepika, correct. Chaitanya, correct. Janvi, correct. So you get the answer, right? So what we are seeing is that as the launches are always done eastward. Why eastward? Because the Earth rotates from west to east. Earth rotates from west to east. This makes launching eastward easier, as it can use Earth's rotation to its advantage. All right. So this is one. So first point, that it is east coast, and the second point, it is near equator. It is near equator. Now, how is this significant? Because the launches, again, here you'll see that the launches are done towards the equator. All right. Launches are done towards the equator. The launches are done towards the equator. And do you know why? Well, why towards the equator? When many of you know the answer. Yeah. So Yashpal, you are correct. Saloni, correct. Janvi, correct. Abhishek, correct. So a lot of you have given the correct answer. So because Earth's rotation speed is maximum. It's almost 1600 kilometers per hour at the equator. So that's why Sriharikota. Now understand one point. Why we are also building Kulasekara. Why are we also working on Kulasekara? Because see, when the launches are being done from Sriharikota, the launches will always be done in a manner that, let's say, from something like this. The launches will always be done like this. Why? We would have ideally wanted to fly like this, but why can't we do that? Because then we will be flying over Sri Lanka. So not only Indian lives matter, Sri Lankan lives are also important. So you cannot say that fine, over Sri Lanka we can fly. No, we'll have to make sure that we don't do that. And because of that, what we do is that what happens is that we cannot really fly directly towards we cannot directly fly towards the equator. We cannot fly over Sri Lanka. We'll have to avoid that. And because of that, what happens then? Because of this, now you have to take a longer route. Correct? You have to take a longer route. So that means extra fuel. That means extra expense and all these problems. So that's why Kulasekara, because Kulasekara from here very easily we can do this kind of a launch without having to fly over the Sri Lankan landmass. So that is why Kulasekara is the next spaceport that India has been working upon. Right? So yes, I mean most of you have given the correct answer. Don't take us lightly, sir. We are Mukesh as geography students. Oh, wonderful. I'll pass this feedback to Mukesh, sir, for sure. All right. So just understand why we are using why we are flying over this, why these points have been chosen, why Sriharikota and why Kulasekara. Right? And Kulasekara has been in the news very recently. Just a couple of months back, Minister for Science, Ministry of Science, he basically was also talking about that we will be trying to build this faster. Already it has been in the works. It's not that it's a new announcement. The announcement had happened many years back, but now we see that we are trying to move positively towards all these things. So that's why this is how we are looking at the launches in India. Now, one very, very important topic, again, a topic which has been very relevant in the past few years, and this is the topic of space debris. Now, when it comes to space debris, understand what space debris is, first of all. So, space debris, also called as space junk, this is any piece of machinery or debris left by humans in space. Now, we are launching so many satellites, we are launching so many missions, and all these missions, where do they go? After the mission is over, they keep on revolving, in the same orbit. They remain there in the same orbit for such a long time, for a very, very long time. So, that's why what happens is that slowly and steadily, the amount of leftovers that we have has been increasing. And this amount of leftovers that keeps on increasing, keeps on piling up, that's causing another kind of issue now. That now, especially when it comes to the low Earth orbit, the number of launches that we do in the low Earth orbit compared to the high Earth orbit are much higher. Because first of all, it's easier to reach there, right? Secondly, we also discussed that the operational period, the operational time of each and every one of these launches, uh, or each and every one of these satellites, they're not really, they do not last for very long, only for 2-3 years, 5 years maximum, and you keep on replacing them all the time. So then the junk increases, and then there are nano satellites that we are launching today, and then we have projects like Starlink project, where they are saying that 10,000 satellites will be launched. So just imagine the kind of problem that this low Earth orbit is about to face, or rather is already facing. So now, when it comes to, let's say, space debris, this is basically the leftover. Overall, when you look at the data, you'll see that it's only 7% of the entire satellites that we have is operational today. We have 65% of the objects in the space which are non-functional objects, and there are 28% which are fragments. So that's why if you look at the data, there are almost 4,000 active satellites right now. There are almost 3,000 dead satellites, more than 34,000 pieces of space junk that are larger than 10 centimeters, 128 million pieces of space junk that is larger than 1 millimeter. So that's why just understand that this problem, the concentration of these leftovers, the space debris, has been increasing day by day, and it is going to make life very difficult in the coming years. And this is where there is a concept which is called as Kessler syndrome. So in case of Kessler syndrome, this is an idea that was proposed by a NASA scientist, Donald Kessler. And Donald Kessler, what he said is that if, just look at this statement, this was his statement, that if there was too much space junk in the orbit, it could result in a chain reaction where more and more objects collide and create new space junk in the process, to the point where Earth's orbit became unusable. So what he said is that there is a possibility in the future, and look at this, that this is 1978, when hardly any launches were happening. So what he proposed is that in the future, what may so happen is that maybe there are two satellites that collide, and because of this collision, a lot of space junk is created. Now there are other satellites which are also in the vicinity. They might also come in contact. They might also collide. They might also get destroyed, and this might lead to a chain reaction. This might lead to a chain reaction, so much so that the entire orbit then becomes unusable. So this is a possibility of the future. Now, for then it was future. Today it is the present. Today we see that already space debris have become a very big challenge for us, and we see that we now have started moving towards cleaning the space debris. Now we have been starting to look at the various technologies that will help us in cleaning the space debris. So, and there are various technologies that India has been working on, or US has been working on, Japan has been working on, European Space Agency has been working on. So there are various different technologies that today we have been working on. Scientists have called low Earth orbit as the biggest dump of waste. So there is no larger waste dump than the low Earth orbit, according to what the scientists have been saying. So that's why now we are moving towards cleaning of the space debris. We want to clean up this space. Now overall, just understand that cleaning up, there are various different ways to do that. So for example, what US has been using as one of the technologies is that they want to launch certain missiles or satellites that will push the satellites away, from the low Earth orbit, so that they can clear off the low Earth orbit. That is one. Then India has something called as Project Netra. India has Project Netra, and this Project Netra is basically another project which will help in clearing the space debris. So ISRO, for its own space debris, the space debris that we are creating, we have this Project Netra. Again, came into contention just a couple of years back, and with this, we are trying to solve the problem of space debris. Similarly, Japan, JAXA, they have made kind of a fishing net. They are working on technology which is like a fishing net, which will just keep on collecting all the space debris in the path. So there are all these different projects that we have been working on today. So you have to know all these things. Just, I mean, from the current affairs perspective, whatever comes up in the later half also will be very, very important for you. Now, apart from all this, there is one more thing, that is India's new space policy. New space policy of 2023 that was just released 2 months, 3 months back in the month of May. So for this, there is a document. And I'll share the document with the team so that they'll share it with you as a part of the additional reading material. There's nothing for me to explain there. There are only certain points which are important. So in the document, I have highlighted the important points. Right, I've highlighted the important points, so only those points go through. Otherwise, there are a lot of things that are written there, so not everything is significant for you. All right, there are only these things that are important, and these are purely factual, so it does not need any explanation from my end. So that's why in the document itself, I have underlined, I've highlighted the most important parts, and I'll share the document with the team, and they'll share it with you. All right. So apart from all these, I mean, any current affairs, for example, whatever happens with Chandrayaan 3, because these are still early days, I don't really want to discuss a lot about Chandrayaan 3 now, because there are too many things that we keep hearing about, all the experiments, all the new data, with what Pragya rover is doing, or what Vikram lander is doing, or even the orbiter data that we have been collecting all the time. So there will be a lot of development that will keep on happening. So just keep on noting it down at some place, so that you have everything related to Chandrayaan 3 at one place. Chances are very, very high that a question comes from there. Because see, Chandrayaan 2, more or less we knew that questions will not come. The reason being that it was not a success mission, right? It was not a successful mission. So chances were less that a question will be asked from a mission that was not successful. But this time, it has been successful. So chances are very, very high that the question will come. Same goes for Aditya L1. Aditya L1 is about to be launched. Once it reaches its orbit, after that, it will become very, very crucial for you from examination perspective. So these kind of things you will have to look forward to and add the information over the course of next 9-10 months. All right. So this is about this chapter. Any question if you have here before we move on to our next? How will Project Netra work? So Project Netra basically is more of a maneuvering technique where we are trying to push the satellites away from its orbit. So that either they fall. I mean, if these are smaller pieces, we want it to fall in the Pacific. We do it in a manner, or we want to push it away so that we can clear whatever we have created in the lower orbit. So in a manner, you can say, in simple terms, it's a maneuvering technique. Chandrayaan's rover has life of 14 Earth days or 1 lunar day. Will it be defunct after this time? Yes. After that, it will, because it's working on solar energy, right? It works on solar energy. So until the point solar energy is available for it, it will be functional. Otherwise, after that, it will not be. give an example of how a question can be asked regarding Chandrayaan 3. See, there are multiple ways in which they can ask a question. A question can be indirect as well. For example, question can be about the development of space technology in India and what is the significance of mission and what are we doing and all that. That is one of the ways. Second could be directly based on the objectives of what the mission is, what it is supposed to do, what will be the potential benefit for us, how does it help India in the future. So these kind of questions can be asked. So mains wise, these are the things. Prelims wise, all these smaller things. That what do you mean by rover, for example? What do you mean by a lander, or the various experiments that it is doing? So they can ask, they can give you the facts about this experiment. I mean, all the data that they are collecting, they can give you the facts about the data, and they can ask what is wrong and what is right. That which of the following are the findings of Chandrayaan 3 mission. Something like this can also be asked, where they have given 3-4 statements. So there are multiple such ways in which they can ask this question. How Chandrayaan 3 is able to send the images and other things. Basically, a communication line is set up between the relay that they are doing, and that relay is then sent back with the help of communication satellites. Whatever be the launch vehicle which is falling into the sea also creates ocean debris, which is harmful for the marine ecosystems. So we have to work on marine debris along with space debris. You're absolutely correct here. You're absolutely correct here that this also has to be done, but we have taken a plan for granted. I mean, this one image that we have here right on the board also signifies that cleaning our planet has been became a priority very late, and right now we already have moved to cleaning the space and have forgotten about cleaning our own planet. So yes, the point that you have raised is absolutely correct. The document that I'm talking about, it's the document, the PDF that ISRO has released. So I'll be highlighting all the points there itself, and I'll share that with the team. Release a solution for creating space debris? Potentially, yes, but it's more for making it cost effective and time effective as well at the same time. How far does the signals work in order to send pictures? I mean, millions of kilometers it can. So that's why coming from the moon, it's not really a big task for us. Because ultimately, just understand this, that ultimately it is based on radio waves, right? The communication setup is based on radio waves, and radio waves can travel very long distance very fast. So that's why we can very easily get it from there, right? So with regards to Chandrayaan 3, the question may or may not be asked. May or may not be asked the question because of the popularity of this. See, we can't say anything. Yes, we have seen in the past that some of the very significant topics have also not been asked by UPSC. So you can't say, but yes, the chances will be very high that they ask a question from here. We have to expect that question comes. If it doesn't come, it's fine, but we have to expect. So let's move on. The next chapter, we'll start with a brief introduction of this chapter. We cannot do a lot today, and we'll continue tomorrow. So energy, as a chapter, energy from the perspective of your examination, from both prelims and mains perspective, it's going to be a very significant chapter, and a chapter from where we expect questions to come from both prelims and mains perspective. Now, if you look at the history of this chapter, you'll find that 10 years back, 15 years back, questions were hardly coming from there. But now we have seen that the number of questions from this part has been increasing. Today, you'll see that every year at least 2-3 questions in the prelims examination, and at least one, if not more, number of questions in the mains examination as well. So in both the papers, both your prelims as well as in your mains papers, the questions now have been coming from energy chapter. What's the reason? The reason is what the world has been doing today. Whether India or the other parts of the world, you find that everyone has been working on potential solutions so that we can move away from coal and petroleum. Right? India has been trying, other parts of the world also have been trying. So we all collectively have been trying to work upon the alternate sources of energy: solar energy, wind energy, geothermal energy, ocean energy, tidal energy, nuclear energy, so on. Hydrogen, a very significant example today. So there are so many examples of where we are trying to use the alternatives, where we are trying to build the alternatives to coal and petroleum, and that is why this particular chapter becomes significant. So energy, first and foremost, what do we mean by energy? Energy in simple terms, in terms of physics, we say that energy is the capacity to do work. Although the work as we define in physics is also very different. But in general, you know that if you have to do something, you need energy for that, right? Anything that you need to do, you need energy for that. To take this class standing here for 3 hours, I need to eat at least the last night so that I can deliver here the result for. So I need energy to deliver this. Similarly, you need energy to focus on your class. You need energy to do well. You need energy to study all day long. But work definition in physics is very different. We say that when you have force and you have a displacement in the direction of force, then only work is done. So for example, me standing at one place for 3 hours or more means there is zero work because there is zero movement. So even if I'm doing everything but standing at one single point, you can still say at the end of the class and pass on a feedback that the teacher did nothing. The work done by the teacher was zero. So in physics you can say that, but in reality that's not the case, right? So for doing anything, we need that energy, right? We need energy for doing work, and that is how we define this. And we know that this energy, it exists in various different forms, right? It exists in various different forms. There can be mechanical energy, where you have kinetic and potential energy. There can be heat energy, there can be light energy, there can be nuclear energy, there are electrical energy, magnetic energy. There are so many different forms in which energy can exist. But what we want to study, what we are studying here, are not these different forms of energy. It's not about the physics of energy, but rather what we are going to discuss are the sources of energy. That what are the various different sources of energy? So the first way in which we classify energy, there are two basic ways in which we classify energy. One on the basis of renewable and non-renewable sources, and second on the basis of conventional and non-conventional sources of energy. So first we'll try to understand what exactly do we mean by renewable and non-renewable energy, and then we move on to conventional and non-conventional. So first and foremost, when we say that something is renewable energy, examples you can see here, you have solar energy, wind energy, geothermal energy, biofuels, etc. They are counted under renewable energy, and coal, petroleum, and natural gas, they are being counted under non-renewable energy. So when it comes to renewable energy, how do we understand that a particular given source of energy is renewable or not? How do we define that? How do we say something is renewable or not? Let's say if I ask you, suppose that you have a source of energy that can be renewed after 50 years. That today you have used it, in 50 years again it will be renewed, and then you'll be able to use it. Do you still call it a renewable energy? That one is fine. That something that is exhaustible, that will completely vanish, is anyway non-renewable. But something, let's say, that can be renewed in 50 years or 100 years or 200 years, would you call it as renewable? Perhaps not, right? Because when you say renewable energy for us should be an energy source that has a constant supply, right? That has a constant supply that we can use as a source of energy day in and day out. So that's why when we say that something is renewable energy, in calling something as a renewable energy, our replacement rate should be higher than the consumption rate. Correct? So the rate at which we are consuming should be lower than the rate at which we are able to replace it. So when we see that replacement rate is higher than the consumption rate, we can say that it is renewable. Correct? We can safely say that it is renewable because we are able to replace it faster than we are consuming. this is what is happening with these sources. And another way to say the same thing, you can say that these are sources which will last for as long as the earth exists. These are the sources that are going to last for as long as the earth exists. So for example, if they consider solar energy, so solar energy is not a source of energy that is going to exhaust, and the day it exhausts will be the day every one of us will also start exhausting. We'll also stop living because photosynthesis can't happen, the plants can't survive. If plants can't survive, animals can't survive, we can't survive, nobody can survive, and that's why that will be the end of the earth. So that's why renewable sources are the sources that will remain with us for as long as the earth exists. So that's why renewable, to define renewable, one of the basic ways to define renewable is for energy source with higher replacement rate than consumption rate. Right? So rate of replacement is higher than the rate of consumption. So this is how we define anything that is renewable. And on the other hand, we have non-renewable sources. So non-renewable, you have coal, petroleum, and natural gas. Why are we calling it as non-renewable? Because once we have exhausted these, once we have exhausted this, after that, it will not be usable after that. It will not be replenishing after that, correct? As long as we have it, we are using it. After that, we can't. And the time that it has taken for the formation of coal or formation of petroleum to happen, compared to that, the amount of... Is there any problem with the class? Some of you have written? Some of you are facing problems. Most of you have written no issues. Just for the sake. For those of you who are facing problems, does the problem still persist? Is it fine now? I had refreshed the class. I just refreshed the class once. All good? Good. Wonderful. So, yeah. So what basically we are saying is that coal, petroleum, and natural gas, when you consider these sources, they have taken a lot of time to form, and for us to exhaust them, we have taken hardly any time. So, for example, if I ask you, do you know how much time it takes for coal formation to happen? How much time does it take for formation of coal to happen? Any idea? Some of you have very small estimates. So it takes almost more than 300 million years, right? So not 500 or 1000, 300 million years. So coal formation could have taken, or has rather taken, almost 300 million years, more than 300 million years to form. How much time have we taken to exhaust it? We have hardly taken 300 years. So something that took 300 million years to form, we have taken 300 years to exhaust it. Estimates for India says that we have almost 130, 140 years of coal left. With the present rate of our consumption, we'll be done with coal in the next 100 years. So that's why what we have seen is that the formation of coal takes a lot more time than the consumption of coal. So that's why these are non-renewable sources. And it's not even that today formation is happening and today tomorrow again it will be available for you. No, there were very special conditions under which formation of coal happened or even formation of petroleum happened, and those conditions do not prevail anymore. So it's not that today also coal formation is happening and 300 million years from now some generations will see coal. No, it will not. It is not going to happen. So that's why these are non-renewable sources of energy. Now, out of all these renewable and non-renewable sources, there is one peculiar case of nuclear energy. That whether should we call nuclear energy as renewable energy or non-renewable energy? What is your opinion? Whole of Jharia in just 20 years. Yeah. The story of Jharia is very heart-wrenching. I come from those areas. I have been to Jharia. Many of my relatives live near Jharia, so I know what the conditions are. All right. So many of you are writing renewable, non-renewable, neither. Okay. So yeah. So let me tell you about nuclear energy and why I'm saying that it's a peculiar case. Now, in case of nuclear energy, we know that there are various forms of nuclear energy. It can be nuclear fission or nuclear fusion. We'll discuss about all these things later. But in case of nuclear energy, right now, nuclear fission is the preferred choice. Nuclear fission basically is the preferred choice, and nuclear fission is how we know how to use nuclear energy today. The electricity production that happens through nuclear energy, that is based on nuclear fission, and nuclear fission is carried on with the help of uranium. It is based on uranium. Now, of course, uranium is also like a mineral inside the Earth's crust, and it is also present in a finite quantity, limited quantity. So that's why, because when we look at the present scenario of how we are using nuclear energy, which is based on uranium, you can safely say that it is non-renewable. If we consider uranium, you can say that it is non-renewable because uranium is finite. So the energy that you get from uranium will also be finite, and hence you cannot say that it is a non-renewable. Sorry, you cannot say that it is renewable. You can say that it is a non-renewable source of energy. Right? It is a non-renewable source of energy as long as uranium is concerned. So when we look at uranium-based energy, then we say that it is non-renewable. But then there are other aspects to it. The other aspect is fusion. And now, with fusion, what happens is, first of all, hydrogen is used. So hydrogen is much more abundant than uranium. And also with fusion, with a very small amount of hydrogen, very significant amount of energy can be produced. So then when we are considering fusion, which is the future, mind it. So it is renewable in that sense. When we are considering fusion, it is renewable. Another way to look at it is pollution. That when you look at coal, petroleum, and natural gas, we know that these all are highly polluting sources. Compared to that, solar energy, wind energy, biofuels are clean sources of energy. So that's why from this perspective, when we are looking at things, we understand that renewable energy are the clean sources and non-renewable energy are the polluting sources. So nuclear energy also is cleaner source. So if you look at from that perspective, you can say that it is renewable. But then there's the other argument, and the other argument is that when you look at when you look at radioactive pollution, so there is no carbon-based pollution, but there is radioactive pollution. So because there is radioactive pollution, should we say that it is a clean source of energy? Perhaps we cannot. Then there is another argument, and that is based on a kind of reactor which is called as fast breeder reactor. And fast breeder reactor will be able to produce more fuel than the fuel that it consumes. So then it becomes renewable. So whether now the dilemma is whether to call it as renewable energy or non-renewable energy. And if let's say UPSC asks this question in your prelims examination, where they have given you a statement, based on the same, where it is being asked whether it is renewable energy or non-renewable energy, just run to the next question. Please don't answer that question, because we don't know what is the context in which they might have asked that statement. So you might mark renewable, they might think non-renewable. So move on to the next question, or as soon as you come out of the examination, just file an RTI that I want to know the answer. So that is the potential solution. Otherwise, I don't know what to do if such a question is asked, because frankly, if you ask me, I don't know how to classify it. Because also understand that there is no convention that defines what is renewable and what is non-renewable and so on, and hence we do not have any idea. So about nuclear energy, we'll have a better discussion when we go to the discussion at a later part of the chapter. Second way to classify is conventional and non-conventional. Conventional source of energy, of course, is the source of energy which we have been using for quite some time. So coal, petroleum, natural gas, firewood, straw, dried dung, etc. They can also be called as conventional, because we have been using it for a very long time. So for example, let's say coal. So we know that significant amount of coal usage started after the Industrial Revolution in Europe and then spread to other parts of the world. A big reason for colonization of Asia and Africa has been coal. But when you go back in history, you'll see that it's not that coal usage started in with Industrial Revolution. Before that also, if you read medieval history of Europe, you'll find that there were some rulers who had banned the use of coal because of the pollution that coal was causing. The smog kind of situation that is a big menace for us today. The smog situation was in Europe, in London, for example, in Britain, even in 1500s and 1400s, and where there were rulers who had banned the use of coal because of pollution and other aspects of it. Some of the first instances of coal mining and coal usage goes back almost 4,000 years back in China. Almost 2000 BC in China, we find some evidences that coal actually was being used already. So that's why these are some conventional sources. Non-conventional are the ones that we have started using only in the past few decades, you can say. So that's why these are non-conventional sources. We have just started using it. We have just understood how to use it over the past few years only, and hence we see that these are called as non-conventional sources. Right? That's why these are called as non-conventional sources. So overall, non-conventional sources, we have solar energy, wind energy, geothermal, biofuel. So you can see that the renewable energy sources, you can see that the renewable energy sources are the non-conventional ones, and the conventional energy are the non-renewable ones. But it's not always the case. Remember this, it's not always the case. For example, let's say if we consider shale. If we consider shale gas, then shale gas is an example of non-conventional, also at the same time being non-renewable. That it is a non-renewable source of energy, but it is also not a conventional source of energy. So that's why it's not always the case. It's not always the case that always conventional sources have to be non-renewable and always non-conventional sources have to be renewable. That's not the case. It can also change. So this is how we classify energy. This is how we classify energy. Now in the chapter, what we are going to discuss is that first we'll discuss about all the conventional sources of energy, and then from conventional sources of energy, we will move on to the non-conventional sources of energy. All right. So this is how we are going to move, and this is how we are going to take the route in this particular chapter. Now, so overall, this is basically what we are going to do in this chapter. So first topic for us is coal. Now, looking at coal, first and foremost, what we understand with coal is that coal is a source. Coal is a source which can be said to be a fossil fuel. Right? It can be said to be a fossil fuel. Why do we say that it is a fossil fuel? Fossil fuel means that it is coming from prehistoric vegetation. Fossil. What is a fossil? Fossil is where you find the remains of ancient flora and fauna. That is fossil. So coal basically is what? Coal is said to be altered remains of prehistoric vegetation that originally accumulated in swamps and peat bogs. So now, when we say that this is coal, when we say that this is what it is, and this is a fossil fuel, and coming from swamps and peat bogs, the formation of coal is supposed to have started on land. It should have started on land. That on the land, all the vegetation that was there in the wetland areas or in the swampy areas, because of some geological or seismic reasons, they would have been submerged under land. And while getting submerged, they were subjected to high temperature and pressure. Right? They would have been subjected to high temperature and pressure, and this subjection to high temperature and pressure would have led to a position like this. Where chemical and physical changes started to happen. So first, all this vegetation that was there in the wetland areas got submerged, and as it got submerged under land, it mixed with the sediments and the silt, etc., that would be there in the deposits. Then high temperature and high pressure it was subjected to. Under these conditions of high temperature and pressure, they got changed physically and chemically, and ultimately led to the formation of coal. So coal basically is coming from prehistoric vegetation in the wetland areas. So formation would have begun almost 360 million to 290 million years ago, and then from there on, the buildup of the silt and other sediments together with the tectonic movements. Right? So buildup of silt and other sediments with tectonic movements buried the swamps and peat bogs often to great depths, and with the burial, the plant material was subjected to high temperature and pressure. This is how we see that the change might have happened. So formation of coal, this is how the formation of coal would have happened. Now, based on the formation of coal, we see that depending on how much temperature, how much pressure, what depth it was buried under, based on all these factors, we see that there are different types of coal. So we have peat, lignite, bituminous, and anthracite. These are the different types of coal, which is based on this, which is based on how much depth, how much temperature, and how much pressure. So first, for example, if you look at peat, for peat, what we see is that it was not subjected to high temperature and pressure. The time also that it has been buried for also has not been that long. Lignite, as you can see, more pressure and heat. Bituminous even more, anthracite even more. And that's why we see that these are four different types of coal. Now, if you look at peat, for example, peat, as you can see here, has a woody appearance, right? Does not really look like your conventional coal, because if I ask you to imagine coal, you will think of a black colored stone, right? So just like how bituminous looks like. So peat does not look like that, has more of a woody appearance, looks like bark of a tree. Now, why? Because it was not subjected to very high temperature and pressure. So complete conversion into coal did not happen. And that's why it is the lowest variant of coal. This is the lowest variant of coal. So much so that if you go to Coal India website or Ministry of Coal website, many times they do not even consider peat as coal, and they would write peat and coal. So coal is coal and peat is peat. So they do not even classify peat as coal many times. So that's why peat, just remember that it was not subjected to high temperature and pressure, and hence it has this kind of appearance, and the efficiency is also very low. Then after this, so not subjected to very high temperature and pressure. Right? So that is what peat is. Then after that, we have lignite. Now, lignite is also called as brown coal. It is also called as brown coal. And why we call it as brown coal is because it has a brownish appearance, right? Looks like coal looks like a stone but has a brownish appearance. So again, not really subjected to very high temperature and pressure, not for very long. Better variant compared to peat, but still not a great variant, still not a very good variant of coal. So that is what lignite is. Then after that we have, and one thing about lignite is that it can undergo spontaneous combustion. Just remember this property, that it can undergo spontaneous combustion. So what is spontaneous combustion? That spontaneous combustion is that when you have combustion happening on its own. When combustion is happening on its own, in that case we say that it is spontaneous combustion. So what happens in case of coal many times, especially whenever you have lignite, that it might lead to spontaneous combustion of the coal. So overall, that's why these kind of possibility is there, that it can, all these things can happen. And many times basically this spontaneous combustion or catching fire on its own can happen, and it can happen whenever, let's say, coal resources are exposed to air or exposed to oxygen. So if you remember, we had discussed in the fuel when we were discussing scramjet, that only having the fuel is not enough. You also need to have the oxidizer, right? You need to have the oxidizer or at least oxygen. So many times what happens is that when it comes to all these things, when it comes to something like lignite can catch fire when it is exposed to air. It is possible. It's not always. It's not always. It can. It can. And hence, in certain cases, this has happened in the past where we have seen that lignite has caught fire. So overall, that's why this becomes a big challenge for us many times to ensure that it does not cause any significant trouble. Then we have bituminous. Bituminous many times is also called as industrial coal. It is also called as industrial coal. So why industrial coal? Because it is the most widely used form of coal. The efficiency is very good, the pollution levels are low. So that's why various industries, whether it is about electricity production, whether it is iron and steel industry or other chemical industries, you'll see that they all use bituminous. And then we have anthracite. Anthracite, of course, is the best variant of coal. Efficiency is very, very high, but not found in as big quantities as we see with others, for example, compared to bituminous. So if you see a basic comparison between all these, carbon content wise, peat is very low, less than 40%. Okay, so carbon content is less than 40%. Then in case of lignite, it is between 40 to 55%. For bituminous, it is between 55 to 80%. And for anthracite, it is between 80 to 95%. So that's why carbon content of anthracite is the highest, and carbon content of peat, of course, is the lowest. So that's why efficiency is very low for peat, and for anthracite it is very high. So that's why, from the perspective of the ash content or the impurities is very high in case of peat and very low in case of anthracite. So that's the basic comparison between all these. So that's why we see that all these are used in various different forms. Use-wise, what we see is that peat is not really used as a fuel more. In industries, etc., it is not used. But in agriculture, it can be used. In water filtration, as it can be used. In all these things, we see that it can be used in all these kind of applications. Lignite can be used in electricity generation. It can be used in industrial processes as well. But largely, it is bituminous. Which is the most important variety of coal for us. And then anthracite can be used in heating systems or smelting, etc. Overall, when you look at the distribution, for example, in case of India, you'll see that the top three states with coal are Jharkhand, Odisha, and then Chhattisgarh. Jharkhand having the highest, and then followed by Odisha, and then followed by Chhattisgarh. But overall, all these areas of central Indian part, Jharkhand, Odisha, Chhattisgarh, Telangana, Andhra Pradesh, Madhya Pradesh, Maharashtra, West Bengal, even parts of Bihar and Uttar Pradesh, these are all areas where it is significantly found. This part altogether is the part where bituminous is found the most. Right? This is where bituminous is found the most. This part of Assam, Meghalaya, and Arunachal Pradesh in the northeastern parts, this is where we find peat more. Although it's not that bituminous, etc., are not found, they're also found, but peat is also found. Peat is found more. Then these kind of areas, Puducherry, Tamil Nadu, Rajasthan, Gujarat, even parts of Kerala, these are areas where lignite is found more. And then this part of Jammu and Kashmir is largely where anthracite is also found. So this is how we see the distribution of coal in India. So overall, this is what we see with regards to coal. Then, okay, let's use this discussion of coal ash, etc. is going to take some time. So let's end our class here. We'll start with coal ash in the next class, and we'll begin from there. Coal ash, coal gasification, etc. We'll discuss, and then we'll move on to petroleum and other sources of energy. Meanwhile, if you have any questions, please let me know. If you have any doubts, please let me know. What is fusion? How is it renewable? We'll discuss about this later. Don't worry for today. Most of the day after tomorrow, we'll have a discussion on it. Happy Raksha Bandhan. Happy Raksha Bandhan to all of you celebrating. Does UPSC ask mining-based questions in prelims examination? They can. I mean, if there is something significant to be asked, they can always ask it. How is peat used in agriculture? See, because peat is organic in nature, so that's why it can help in organic buildup in the soil, so that you can enhance the quality of the soil. So even, for example, I mean, if especially, let's say, if you are into gardening and if you have house plants, etc., if you go to a nursery and buy house plant, etc., you find that they give you peat. They will give you peat. Even if you go to Amazon and if you type peat, you'll find that how peat looks like, and peat can be used for gardening, etc., in the house. How the Big Bang nucleosynthesis acts as evidence to the Big Bang theory. See, Big Bang theory says that the start of the universe, just after the formation of the universe, just almost 10 seconds after the formation of the universe, hydrogen formation had begun. And for the next 3,80,000 years, a lot of hydrogen and helium was formed. So that's why, according to that analysis, according to that assumption, also in the manner you can say, whatever has been explained, it says that hydrogen and helium should be abundant. And then later we found that yes, they are abundant. So that's why they become, this Big Bang nucleosynthesis becomes one of the evidences that supports the Big Bang. Tomorrow is holiday. No, there's no holiday. Fuel fabrication. Fuel fabrication is making the fuel, creating the fuel from the chemicals that you have available with you. If the rate of dissipation of heat is slow compared to the evolution of heat at a certain time, temperature reaches the ignition point of cool. That's correct. And that is what happens in case of lignite, while the self-oxidation, as we call the process, the self-oxidation takes place in this manner. How many sessions for science and technology? Total of 11 sessions will be there. Today we are in the third session. Hydropower, renewable or non-renewable? We call it as renewable. In my state, Odisha, in Talcher, as per the coal reserves, it has been in the state that the government authorities are giving directions to move or vacate the areas of near coal mining. Why? I'll have to check what exactly has happened. I know the context of Jharkhand and what has happened in Jharkhand, but what exactly is happening there, I'll have to check upon it. Is the convective zone in liquid form? It is in ionized form, mostly gaseous. What should be the revision strategy? So revision strategy is it's simple that whatever we are doing in the classroom, please go back and revise it. Try to recall things on your own as well. Try to write something on your own. Try to write answers also on your own, and that will help in your significant improvement in your learning patterns. And then if you have any doubts, you can always bring it back to us. But the revision also should happen at least twice or thrice, and you cannot just do it once and wait after that. So just remember all these things. Does Moon's L4 and L5 points also have Trojan? No, because those are very small points, so it's not easy to do that. Why does the temperature rise from chromosphere to corona? As I told you that we do not really know the exact reason why something like that happens. About the recordings, as some of you have been saying, it's not in my control, but still I can talk to the team, but can't see anything on it. Right? Which coal is used to produce thermal energy? It's largely bituminous that we use. In India, which kind of coal is most abundant? It is bituminous. Bituminous is the most abundant in India. Subbituminous. Subbituminous basically is a kind of bituminous also called as steam coal, etc., which is used largely in the industries. I'm appearing for 2024. Do I need to cover current affairs from January 2023? More like I would say, I mean, conventionally from July also if you start, that's fine. But to be on the safer side, even if you start from March, that's enough. January is not required. How peat is used for water filtration? Because it can absorb or attract particles towards itself, so it will be able to clear off a lot of particles. All right. So let's end the class here. We'll again meet back tomorrow. We'll start with coal ash and then we shall move towards the other topics as well. Till then, please go back, revise everything. If you have any doubts, please bring them back and we shall discuss that tomorrow. Thank you very much.